with Alexei with his second talk on nonlinear quantum optics.
Thank you. Hi, everyone. Good morning. I hope the French folks are a bit more rested than yesterday. So before I move to the second part of this lecture, let me just recap what I said yesterday. So yesterday was a bit of a tutorial about nonlinear quantum optics, and that was essentially discussing the most of that lecture was about how to couple flying qubits, that's optical photons, to static qubits of various kinds. Okay. I told you that if you just send a photon on an atom, that process is fairly inefficient because the cooperativity, which you can also define in free space, is going to be something that scales as the surface of the atom, the effective scattering cross-section, that's lambda squared, divided by the surface of the photon, which is typically the waist squared on which you focus your light, right? And I told you that to make that number larger, there is several strategies possible. One consists in putting this atom in a cavity, in which case this cooperativity is multiplied by the cavity finesse. So this is the inverse of the total losses. Or you can use Rydberg interactions and replace this single atom by what people call a collective superatom, where there's an ensemble of emitters that act as a single emitter because of Rydberg blockade, preventing multiple excitations from appearing in there. And in that case, the cooperativity is multiplied by the number of atoms and not the finesse. So it's as simple as that. Now the big question here, of course, is what are these numbers, how big we can make them, okay? The cavity finesse, for all practical purposes for quantum optics experiments where you want to get photons in and out of the cavity, so far, we can get to numbers around 10 to the 5. I'm looking at Romain to confirm. Yes. You can make cavities with something like 10 to the 6, but in that case, when photons are lost eventually, they're lost in the environment and not in the mode where you're actually collecting them. So this is the typical number which is limiting you here. When people started thinking about Rydberg superatoms, what they had in mind is that, okay, the Rydberg states that we can reasonably access without too much hassle. We can make better if you want, but typically the Rydberg blockade range is something like 10 microns. Density in a dense cold gas, say Bose-Einstein condensate, you can push it up to the 10 to the 15 atoms per cubic centimeter, so it's 1,000 atoms per micron cube. So you can expect this factor to be this to the cube times that, something like 10 to the 6. And okay, it's not much bigger than that, but it's already bigger than that, and that's just a start. That was, unfortunately, extremely wrong. It was extremely wrong because people forgot about a phenomenon that they rediscovered on that occasion. When you start increasing the density, so this is my Rydberg superatom, and I'm stuffing atoms in there. I'm putting a lot of them. What's going to happen is that at some point, I'm going to have atoms of my Bose-Einstein condensate or of my gas, it doesn't have to be a condensate, entering inside the Rydberg atom itself. The Rydberg range, the real blockade range in this physics is what we're interested in. It is a big number, it's these 10 microns. But the Rydberg atom itself is something that's big too. Remember I told you it's almost an ion, it's an electron that flies far, far away from the nucleus. And for typical numbers people use, this size of that Rydberg atom is about 1 micron. So as soon as you have more than 1 atom per micron cube, you have atoms entering inside the wave function of a Rydberg atom. It's a very interesting process in itself. People in Stuttgart in the group of Tillmann Pfau have been studying that for ages now, doing very beautiful cold molecules. But for quantum optics, it's a disaster because that limits the density before that process appears and everything starts decohering to something like 1 micron per 1 atom per cubic micron. You can maybe gain a factor of 10 or so, but not much more. So the number of atoms here is going to be typically 1,000, maybe 10,000 if you work hard, but it's not going to be 1 million, which is bad news. Okay. There's other bad news, but this is probably what's the worst news in that story. So we knew that when we started. And so the idea we had was to try to combine this and that to get the best of both. Get both the finesse and the number of atoms multiplying our operativity. For the younger people in the audience, when you have these kind of ideas and you think, oh, why didn't anybody think of this before? Usually it's because when you try doing this, you get the worst of both. And that's what starts by happening usually. And then after years of work, you finally get it. So I'm not going to go through the years of worst where we had the worst of both, but works. So just to make things a bit clearer on the next slide, here, if you remember yesterday's story, things work because of the strong coupling between the atom and the cavity. Here, things work because the cloud was either transparent or opaque, depending on the state, the number of Rydberg excitations. So I was switching on and off Rydberg EAT, electromagnetic induced transparency. So how do these things combine in a single setup? So what you do is you make a small cloud of atoms inside the cavity. I made it funky like that. And you arrange your parameters so that if your ensemble has no Rydberg excitations, all the atoms are in a ground state, this laser makes it very transparent. It's the story I told yesterday. When there's no excitations in there, my photons just go through as dark polaritons. If these losses in this cloud are much smaller than the transmission of this input-output coupler, in classical optics language, your cavity is optically overcoupled. So the optical impedance of that cavity is very high, very low, sorry. So the field bounces from here with a phase zero. It's just this simple formula which you can derive on the back of an envelope. If now I put a Rydberg excitation, I have to raise my parameters so that the losses in that ensemble become much larger than this transmission. And in that case, I get a sign flip just thanks to that formula, L becoming much larger than T. So this is how in these kind of systems you can get a phase shift on the light conditional on the state of the superatom, just like Gaudium and his colleagues got a phase flip depending on the state of their single atom in the cavity. So this is the mechanism we will typically be aiming at. Now, what that gives you with respect to a single atom, well, in this case, because you have like 1,000 atoms instead of one, as I just said, you can use a cavity with a much bigger volume, with a smaller finesse, and with a funny geometry which I just represented. And that makes it easier to trap and to cool atoms inside. It's easier to fabricate. You don't have to have super high finesse mirrors, high quality mirrors, and you can do more funny physics if you can have a cavity with a funny shape. You don't lose your photons anymore because in each of these cases your photons bounce off the cavity. They're not scattered in free space. They don't get entangled with the photons that you collect, so you don't have purity losses and so on. The absorption in that cloud has to be compared to the transmission of that mirror, which is, well, typically in our case about 1%. So these losses have to be only about 1%, not 1, which means that you don't have to have a super high density cloud. You're no longer limited by these collision processes which I just described. With respect to free space experiments with these ensembles, your cloud can be smaller than the optical mode. Of course, in free space, it doesn't work. If your photon is much bigger than your cloud, it just goes around and nothing happens. In this case, you have to shift think in terms of cavity modes. The mode that is transmitted in this case, for example, where my cloud is smaller than the mode of the cavity, has a dip in the center. If you decompose that mode in the fundamental and this first excited mode, and if this first excited mode is not resonant, this process is very strongly suppressed. And finally, the fine details of the interactions between the atoms, which I kind of put under the carpet, telling you that it was supposed to be van der Waals, one of our 6, which in real life it is not the case. At short distances, it's actually a horrible mess. It doesn't matter that much in that paradigm as long as you can shift from that regime to that regime.
Sorry, just what is the length of the cavity we are looking at in this kind of scheme?
So in our particular case, the 2 pairs of mirror, which is actually that's what we have in the setup, they're spaced by 2 centimeters. So it's big. So that was actually the next slide. I'm not going to dwell too much on the experimental setup. but I was just going to give you a few details on how these things can work. We have a small cloud of cold rubidium that we prepare here. We do that by loading a 3D mod, then compress it, cool it down, transport the atoms optically in here, and do degenerate Raman sideband cooling, thanks Raman, to make this cloud small and dense. Okay? Once that's happened, this cloud sits in the middle of this 4-mirror cavity, which is, as I just said, 2 centimeters long between this block and this block. The mirrors are 1/4 inch, so that's 6.3 millimeters. It's small, but not that small, depending. The finesse is not that high. The transmission of this input-output coupler is about 1%. You have the numbers here if you're a specialist, so that basically tells you that we are in a collective strong coupling regime with a cooperativity in the 10-ish range so far. Just as something you can do with this kind of big cavities that you cannot do with a tiny Fabry-Perot, you can put 2 of these mirrors on translation stages so you can move them back and forth. If you move them in the same direction, you change the length of the cavities, so that allows you to make it resonant or not for different transition processes that you maybe want to using. If you move them like that, the cavity length stays the same, but what you change is the splitting between the fundamental and the transverse higher excited nodes. So that can allow your photons to jump from the fundamental node to higher excited modes or not, depending on the experiments you're doing. So we had set this up, and then we of course had to check that we could still use this cloud as a qubit. So the first thing you do with a qubit is you drive Rabi oscillations to see if you can make it oscillate between the fundamental and the state 0 and the state 1. In our case, the state 0 is all atoms in a ground state, and the state 1 is one delocalized Rydberg excitation, the things I mentioned yesterday. And we just do that using a pair of lasers that are going to be off resonant by about 500 megahertz from this first excited state in rubidium, which is the 5p3½ in that case. We switch to 5p1½ now. And then you have to detect the state of your qubit. That was one of the other Di Vincenzo criteria. For doing that, you shine light through the cavity, and you see if your Rydberg EAT is on or off. If your cloud is in the ground state, you send a weak probe here. Essentially, you think that you're sending photons one by one. The cloud is transparent thanks to that blue laser, and the photons just go through. Now, if that cloud has a Rydberg excitation, photons are blocked, and you just see a sharp drop in the flux of photons going out. Now, again, I'm not going to dwell that much on this stage we're using. The reasoning behind the Rydberg stage we choose is that we want to have strong interactions between atoms in the state R. This is my qubit state because I want this to be a qubit. I want to have only one excitation, so I want to have a strong blockade. I also want to have strong interactions between atoms of my qubit and this probe beam. So I have this red probe that I'm measuring with this laser that couples me to the state R prime. And I want to have strong interactions here and here between those two guys because I want to be detecting the presence of these states strongly by looking at the blockade of this one. But I don't want to have interactions between R prime and R prime to be very strong because I want to be sending photons in there as fast as I can. And I don't want to have strong self-blockade effects between these photons. So this is why we choose them. These states have a so-called first resonance between them, so we can play with that. It works. So in this case, when we measure the photon flux, we see something finite. In this case, it's dropped down by a factor of around 20 until the atom decays, and then we get back to the initial one. And then we just measure the flux for about 10 microseconds and make these histograms and just decide that we have some threshold around 5 photons. If we have fewer than 5 photons, then we are probably in that case. If you have more than 5 photons, we're probably in that one. And that gives us a single-shot measurement of the state of our qubit with an efficiency around 95%, which is not super high, but it's okay for a beginning. So we can control the qubit, we can measure the qubit, and then we have to check that we actually have succeeded in what I told you just before in getting these conditional phase flips on the light. Yes, sir. Here, this is a histogram of the number of photon counts that we had in 12 microseconds. I'm shining a weak probe through my cavity. the state of that qubit is either 0 or 1. For 12 microseconds, I count photons, and I plot this histogram depending on the state that I initially
Plot
prepared.
the photons in the transmitted side, like that
Yes,
side?
it's transmitted.
Transmitted.
The detector is here.
Okay.
Yeah, it's transmitted.
So would it act as a like two-level system? You are saying, what is your goal to understand? Like in comparison with single atom, so single atom, if you strong coupling regime, you will have like
Yeah.
perfect reflection when they match the resonance condition.
It's exactly to check that we can do the same thing as people can do with a single atom. So when the single atom is not coupled to the cavity, light goes through. When the single atom is coupled to the cavity, light doesn't go through, and that allows you to detect the state of that atom, if it's coupled or not coupled. We want to check that we have the same thing here, depending on the state of the superatom. So next thing to check, again along the lines of, can we do the same thing as people with single atoms in the cavity? Can we get a phase flip depending on the state? Because if you look at the light that's reflected from the cavity, the phase of that light should flip depending on the state of this atom or the superatom that I have in the cavity. I just explained that a few slides before. We do see that. Now we send light on the cavity, we look at the reflection, we measure the phase using a homodyne detector, and we do see that we have a phase flip here in the middle, so which means that we arrange our parameters in a way that it was designed for. Okay? So that was just checks to see that our system can do the same things as single atoms. Now, what when we started doing quantum optics with that stuff, the first experiment we did was to prepare a superposition of ground and excited states of my qubit. Yes?
Instead of 3?
Sorry?
Why did you need 4 energy level instead of 3, like
Oh.
R prime? I could not follow actually.
Sure. Let's say that I have a qubit that I encoded between here and here.
Yeah.
I want to see if my qubit is here or here. Of course, I can just ionize it. I mean, back in the old days, in the experiments of Serge Haroche, or basic, like old experiments with Rydberg atoms, and people still do it, you just try to ionize, and you see if you have an ion or not. These guys gets ionized, this one doesn't. But that's slow-ish. We wanted to have an optical method. And so to have an optical method, you have to check, you have to rely on this EAT process where photons go through or not. Now, if I only have 3 levels, if I start probing that transition, I will immediately depopulate this thing. So I have to leave that population untouched. I should not couple to that level. And which means that I need a 4th one because, like, okay, this one's used, I can still use this one is used, I should not touch it. I need an extra Rydberg level to see that, to detect the presence of that one. I don't know if I'm clear enough on that point.
But you said earlier, like with 3 level, I can get EIT like structure.
So we have, in that process, once we've prepared the qubit, it just sits here or here. You forget about these arrows.
Okay.
And then we have a 3-level EAT here. And that 3-level EAT, if the initial state is here, then it works. If the initial state, if I have a single excitation in R, then that guy gets shifted through the interactions, and the EAT disappears. It all happens because the interactions shift that level. And these interactions are here when the qubit is in R, and they're not here when the qubit is in G. Okay?
Okay, thanks. Yeah.
So, what can you do with this thing in terms of quantum optics? You prepare a qubit in an arbitrary superposition of ground and Rydberg states, okay? By just shining a pulse with a given duration that's going to define your angle theta here. And then you map whatever was in a Rydberg state to a single photon. And if you remember my story from yesterday, you do that by adiabatically rotating this dark state, this dark polariton in a gas, from being a Rydberg excitation to being a single photon. This is my dark polarity from yesterday, where these components alpha and beta, I can just play with them through the intensity of this readout beam. Okay? This is the preparation, this is the readout, and my photon goes in the cavity, and because everything has been designed to be reasonably efficient, I see my photon going out here. And if I make my angle here maximal, when I make a pi pulse, I can get this photon out with a 60% efficiency, which is quite good for these kind of systems. First of all, of course, we had to check that it was a single photon going out by measuring a G2, just splitting this beam and sending on 2 photon counters. We had a G2 around 2%. Then it was actually dominated by some spurious light. It's better now. It's about 1%. And then, because that system was fairly efficient, we could take this photon, send that on a homodyne detector, and make a full homodyne tomography of the state of the pulse that was going out. And we could see that for a small rotation angle, that pulse was slightly squeezed in this direction and stretched in that one, so that's below vacuum. And then it deformed and developed a negativity in the Wigner function that we could measure. So that was a completely deterministic process that worked each time you press a button. So the efficiency of the detection in that mode was also 60%, which means that our photons were indeed like single mode in that case. And the reason why that was 60% is, if you remember the story of yesterday, 90% of cavity extraction efficiency. This is how well we can get the photons out of the cavity. It used to be 95 before we had some crap on the mirror. The 93% of this 2C over 2C plus 1 factor, which I mentioned at length yesterday, and then 2 things that I'm going to be discussing in much more detail in a minute. Okay? This is going to be the fun part. The cloud is either here or here. It's a gas of atoms. It's about 1,000 rubidium atoms with a size of, with a Gaussian radius of about 5 microns. So it's, in theory, completely blockaded because a Rydberg blockade range is about 20 microns. Yeah, it's a single excitation. Now, how well is that single comes in a minute. It's more surprising that you would think with the back of an envelope calculation. So far, let's pretend it's a single excitation. Okay?
So what happens to that bound state of the, like last time when you were talking, there was kind of like this 2-photon bound state kind of.
Yes.
What happens to those here?
What happens to, we would have these bound states, and our colleagues in the Weizmann have them, they make them on purpose. They take a much bigger gas, which is much bigger than the blockade range. In that case, you can have a photon that makes a bubble here, and a photon that makes a bubble there, and they see each other because each of these bubbles deforms the optical index around it. Each photon traveling through the gas changes the optical index in a small volume around it, and these variations of the optical index make a potential gradient, so they...
Okay, so if I understand, you have to like enhance the cloud, you are saying? Is that?
You would have to see these effects, you have to make a long cloud. We have a very short cloud, so we don't have this. One thing which I learned from that experiment, that stuff, that's what we were aiming for. That was not a big surprise. That was very pleasant, but not very surprising. One thing that surprised me, maybe it shouldn't have, was the following. We started fitting this data. So if you remember, I told you here that we could see some squeezing on this quadrature. So we started looking just at the variance of these things. We measure the mean field, mean quadratures x and p, and the variance here and here. It turned out that we could use these numbers to make kind of an alternative for Ramsey spectroscopy. See, you have a qubit. You have a 2-level system, yeah? A qubit, if you remember your undergrad classes, has 2 ways to decohere. It's either decay or pure dephasing. Decay is you go from upper state to ground state, and dephasing is the upper state gets a wrong phase. Okay? And to measure that, what I had learned back then is that you have to do Ramsey spectroscopy. You make a pi/2 pulse, you wait, your dephasing moves you somewhere and then you make another pi over 2 pulse, and you see where you end up. It turns out, so that's how Ramsey spectroscopy works. It turns out that you can do the same thing just by looking at the quantum statistics of your light emitted by your emitter. And that's just because decay and dephasing don't do the same thing to squeezing. If you start, so this is my vacuum field of the mode I'm looking at. I squeeze it, it goes like that. Then what decay is going to do is it's going to bring it back to vacuum. But it's always going to stay squeezed slightly. What dephasing is going to do is going to do that. And so my squeezed quadrature is going to get polluted by the anti-squeezed one. And it's not the same effect. You can get above vacuum noise in that case. So you just take your data, you fit it, and from that fit you extract both the decay rate and the dephasing rate. And then you get numbers that are very consistent with what we can measure by Ramsey spectroscopy. It's just kind of fun. Of course, people don't do that because for this approach to be efficient, you need to collect your photons efficiently, and not many systems can do that. Okay? But it's fun.
Is that more sensitive when you have more squeezing? Because the squeezing
Yes, sure.
you have is just an effect of having just a bit of one photon. It's not very squeezed.
I guess it would. Yeah, but you would have to have a more complex system than what we have. You would have to have multiple excitations if you want to have more squeezing. Yeah.
Very stupid question maybe, but if the light is not squeezed, can I somehow then extract out these two decay rate?
If the light is not squeezed,
Yeah.
I guess you can, because at some point, if you look here, in that part of the graph, it's no longer squeezed. So this is my squeezing, actually. I'm plotting. What the squeezing we get is not much. It's just like 4%. What we do is we prepare a qubit with different superpositions of ground and excited states. We make it emit light, and then we measure the mean field and the variance. And by just fitting the mean field and the variance, you can get this decay and dephasing. I use squeezing because it gives a nice explanation, but squeezing doesn't have to be there.
Okay, thanks. Yeah.
You're welcome. I'm never going to make it through my slides, but keep going with questions, okay? So now I'm getting to things that we've been doing more recently, and that's less of quantum optics and more of fundamental physics. I'm a very, I'm not a quantum engineer, I'm a physicist, so I'm very much attached to studying things that don't work properly, because that's where I learn things. I spent the first half hour, almost like 25 minutes of the day, advertising Rydberg superatoms, saying how good they were. But I mean, there's many physicists in this room, and even non-physicists realize that simple things work easier and better than complicated ones. If you have a simple machine to do the same task, you should use a simple machine. It's going to break down less often, okay? So I have a single atom is a simpler machine than a complicated superatom with 1,000 atoms in there. So there has to be a price to pay for that complexity. And I'm going to spend the rest of my talk explaining you that price. So the things that work less well in that regime and what you can do about them, how you can at least understand why that happens, okay? So we try to use this thing as a qubit. Qubits, as you all know, must be coherent. And one thing you have in this ensemble is inhomogeneous decoherence. Take whatever you like. It doesn't have to be Rydberg superatoms. It's just a collectively encoded excitation. Because these emitters in real life are going to be all slightly different, and in real life it can be because your atoms are sitting in a crystalline matrix and they see a different strain, or because your atoms are sitting in a trap and they see position-dependent light shifts, or because these atoms are not infinitely cold and they are not infinitely cold, and they move left and right, and so you have some small Doppler shifts. The state that you initially prepared, where all these factors are 1, evolves into something where all these factors become different and random. And that means that the state I prepared in my ensemble that one, decays or goes away in an ensemble of states that are no longer in my qubit subspace. This state is coupled to my cavity. It's super-radiant in my language. These states are not coupled to my cavity. They are sub-radiant, or they're dark, or they're asymmetric with respect to my excitation scheme. That the word you use depends on the community you live in, okay? That process exists. It is one of the dominant issues that people have and we have. So we have at least to include that in our models to tell us how well the system can work, how to turn on knobs to make it work better. Now we started doing that, and the first idea you could naively have is that you take this thing, you assume that you prepare that state, and because we have about 1,000 atoms in this ensemble, I have about 1,000 states out there. So it looks like when it starts decaying, just rounds away along that chain, and that's an irreversible process, and I could just describe that by a loss, which is going to be, for moving atoms, just the velocity of the atom divided by the effective wavelength of my spin wave, because that's the only number that comes out of the equations. If you do that, it's a very sensible thing to do, but that will tell you immediately that the excitation that you prepare should decay exponentially. You just put that in a Lindblad master equation and you get an exponential decay. If we do the measurement, we see that this decay is not exponential. It's kind of rather like a Gaussian. It's not a tremendous surprise because, of course, if you do that calculation a bit more carefully, you can say that if at t equals 0, I snap my fingers and I prepare that state r equals 0, and I just wait, do nothing, then my atoms are going to be moving with a Gaussian velocity distribution because it's a thermal cloud, it's a Maxwell Gaussian distribution. And what I see here, the overlap with my state with the initial one, is essentially a Fourier transform of a Gaussian, which is, again, a Gaussian. That's an explanation that's completely sufficient in cases where you can snap your fingers and prepare R0, and that's what happens often in quantum memories. But it's not sufficient when your system is driven by a sequence of complicated pulses, which I had just shown before, where you actually need to include that process in some kind of master equation and still describe the non-Markovian character of the thing. You do have mathematical methods that are generic for describing open non-Markovian quantum systems. I had a look at it when we started, and people couldn't even agree on things, so I decided that I had to do something on my own. So what I've done was to restart from that problem, assume that I have some inhomogeneous spectrum, some distribution from a frequency, from a Doppler shifts or strains in my crystal. I normalized all the frequencies by the width of this thing, and I have some freedom for choosing how I define that width. So my initial Hamiltonian that I want to describe is this guy. It's a sum over all the emitters with these different frequencies xn. Now what I do is to assume that I have many, many, many of these emitters, and I can take a continuous limit. And in that continuous limit, it turns out that this thing can be mapped to an operator which is mathematically equivalent to a position operator in 1D or to a displacement operator in phase space if you are a quantum optics person. It's just math. You don't even have to do that. It's just convenient to think about this way because we know how these things work. Now, if you do that,
Xn here?
x?
Yeah, Xn in the summation.
Xn. N is the atom that I'm looking at. I have 1,000 atoms. N goes from 1 to 1,000. X is a normalized frequency at which this atom resonates.
Okay.
Ideally, they should all be 0, or all be equal if you want. It doesn't matter. But actually, they do follow this distribution here because they have some finite temperatures, some finite Doppler shifts, some finite strain in the crystal, whatever you have.
Yes, but somehow I could not understand this arrow. You are transforming the spin operator to boson operators, or?
So I'm assuming that I have many, many of these. I'm taking a continuous limit, so instead of summing over n, I'm integrating over space, and then I'm basically shifting to a description where I'm looking no longer at a specific atom, but at a specific energy in my ensemble. It's essentially mapping. I'm putting a few things, no, I'm skipping a few calculation steps here.
Okay, I'll
I
ask
know.
you later then after
You'll-
the talk.
But it's essentially a mapping of this discrete Hamiltonian to this continuous one. I transpose, you'll see where the density, where these shapes reappears. It's going to be reappearing in the state that I excite. Okay? So, I say that this is the first state that I excite to make, to match my physical measurements. Its wave function has to obey this. The modulus square of my initial state has to match the inhomogeneous spectrum because this is the probability with which I can found a given frequency in my ensemble.
So, Alex,
Yeah.
you have about 5 minutes and then questions.
Okay. I'll not rush you too much through that, but I'll try to get to the end of that story at least. So this is my fundamental state here. It has to match, the modulus square has to match my spectrum because it's the probability for finding a given frequency in my atomic ensemble. And then I just construct the ladder of these states by applying my Hamiltonian. My first state is coupled by that Hamiltonian to a state that I find by applying that Hamiltonian and orthogonalizing things. And applying that Hamiltonian, this is where things look nice in that picture. Applying that Hamiltonian to that wave function is just multiplying that by x. And then I end up with a polynomial of degree 1 when I do the orthogonalization. I do that a second time, I get this initial kernel times a polynomial of degree 2, etc., etc., etc. So at the end of that day, I'm looking for a family of polynomials that are going to be orthogonal under this weight function, and this is an easy mathematical problem, right? Now, so I do that several times, 1, 2, 3, 4, 5. I get the energies of these states, I get their couplings. And then, so I use a few of these states to describe the non-Markovian character. It's used as kind of like a memory, which can send my information back into my system. And then I say that, okay, I have enough of them, because I don't want to go to infinity, to describe my measurement with sufficient precision. And whatever is left behind, I just treat that as a memoryless continuum for which I can calculate the decay rate and the lamp shift through the resolvent formalism, and that actually takes 3 lines to get this recurrence between this lamp shift, the decay rate, and the elements of my Hamiltonian that I just calculated before. It works quite nicely for Doppler broadening. In that case, the fundamental state is a Gaussian because the spectrums are Gaussian. The polynomials you get are Hermite polynomials because it's Hermite-Gauss functions. The Hamiltonian itself is just A plus A dagger in a Fock basis, so it's very simple. And then you can do everything analytically and get that you have no lamp shifts and the decay rate is not that ugly. So if you put 3 states in your model, you produce your Gaussian quite nicely. You can do that for atoms in a trap, and that works too, even if the initial state is a bit more complicated. And this is where I
So I have one question. Is this driven system or not driven system?
So far, what I've been explaining is not a driven system. It will become a driven system in the next slide.
So you have that EIT bin, or you are not
In this case, I just create that excitation and do nothing. I wait. I create that excitation and let it evolve and decay in that space of asymmetric excitations, okay? I'll use the last minute of my talk because the questions have been interleaving. To tell you something that was a surprise. Now the system becomes driven. When I'm writing these things down, I just decided to make a consistency check and see if my model predicts what I think it should predict in a case where my qubit is driven between the ground state and the excited state with some Rabi frequency omega. And I assume that this omega is strong enough so that I can do at least a few oscillations before the decay happens. Otherwise, it's not interesting. What I thought would happen was inspired from what I knew from normal qubits. And in a normal qubit, if initially if you excite it, it decays along this black line. If you start driving it, it starts oscillating. And if you drive it strongly, it's going to oscillate like this blue curve or red curve, played with different models. And the envelope of that curve is going to be 2 times slower decaying than the black line. And this factor of 2 only comes from the fact that half of the time the atom is in the ground state where no decay happens, and half of the time it's in the up state where it decays. I thought it would work the same way, roughly, for my own Gaussian spectrum. It turns out that it didn't. As long as you do that, you just change the shape of the spectrum, you keep all the parameters the same, and you get oscillations that go practically infinitely. So I thought I had a bug in my code, and then I figured out that I didn't. So I just sat down with a pen and pencil and rederived the asymptotic expression of this thing. And indeed, the decay becomes exponential, and the exponent of this guy is exponentially suppressed itself with the intensity of the driving field. I found that surprising, but of course I rediscovered later that people knew that in a different context. You could do that with a different spectrum for the light shift. The initial state is complicated. The process is not that efficient. They actually have a sum of 2 terms. One that decays a bit faster than here because the exponent is in the field, not in the field square, but still you have the same effect. The other one doesn't decay at all. Why that happens is because in the Markovian case, you start driving your qubit, your states are split, you get 2 coupled states, G plus or minus R. These states are going to be split by omega 2, but they're always coupled to a continuum because this continuum is infinitely large and the coupling is always the same. So they always decay resonantly. In this case, you're not coupled to a continuum directly, you're coupled to a state, and when you split these states, this coupling becomes off-resonant. In this case, this state has an asymmetric wave function in my space, so this guy decays in the tail of this one, and this guy has nowhere to go. Turns out it works. I'm going to stop here. We've measured that in the experiment. We can extend the oscillations of our qubit by a factor of about 14 beyond the natural lifetime due to this dephasing. What limits this factor of 14, why is it 14 and not 1,000, is something that I'm not going to have the time to talk today, but I have a poster outside. You're welcome for questions. It's Rydberg blockade. If we drive the qubit too hard, we force multiple excitations in the cloud. And everything breaks down. How that breaks down was something that I'm going to keep for the next time or for the poster sessions. Thank you.
Let's thank Alexei for the part 2 of his talk. So questions, Sadiq?
Yeah, so is there a specific reason why your cavity, the 4 mirrors are non-planar?
Yes, there is. There are multiple reasons, and there's actually an amazing reason that I didn't think of. When I designed that thing, the reason was that I wanted my polarizations in the cavity to be circular. If you make that mirrors twisted, that naturally happens. And the circular right polarization and the circular left polarizations don't have the same frequency. And they're split by about 80 megahertz. And that decreases your backscattering quite a lot. That also makes the modes that go out of that cavity much more Lager-Gauss. They're much more round than when the cavity is flat. I wanted to have a 4-mirror cavity and not a 2-mirror cavity to avoid standing waves, so that when my atoms move left and right, it doesn't matter that much. One thing I didn't think of, and Jonathan Simon did, was that in that twisted cavity, you get a geometric rotation effect, which means that when your photon makes a round trip, like you send an image in a cavity, and after a round trip in the cavity, it gets slightly rotated. And that rotation acts as an effective magnetic field on your photons. Now, your photons, if you look in a transverse plane at the focal point, if you put your Rydbergs there, they're going to act as an ensemble of particles living in a 2D subspace, which is given by the transverse modes of your cavity. You get this synthetic magnetic field that makes them rotate, and you get interactions through Rydberg, and you can use that to simulate quantum Hall effect related physics. That's not my business. That John Simon in Stanford doing this. That's really beautiful.
Yeah, I wondered if you could sum up what are the limitations of superatom. You mentioned inhomogeneous broadening and Rydberg blockade.
Yeah, okay. Speeding up, this is the explanation of why what we see is not the same thing as spin echo. Ask questions if you want. blockade. The three limitations that I had on my slides are here. Imperfect blockade, stored in the poster, sorry. And the last one is the fluctuations of the number of atoms in my ensemble, because when I load my cloud from one shot to another, I don't always get the same number of atoms in there. And this the number of atoms is involved in the Rabi frequency that we have. The Rabi frequency is the Rabi frequency of each atom. We suppose it's the same times square root of n. If n fluctuates, the Rabi frequency fluctuates. So when we think we made a pi pulse, sometimes we overshoot, sometimes we undershoot. This is fluctuation. I mean, this is problem number 3. Solving that is just about counting atoms, but counting atoms in that particular case is a bit like herding cats. Once you've counted up to 30, the first one is gone somewhere. So.
Hi.
Yeah.
So in the case of this readback cloud, you said mostly you are detecting single photons,
Yeah.
I guess through G2 of anti-bunching there, right?
Yep.
But in general, for single atoms, by controlling the driving,
Yeah.
one can even play with the statistics of the transmitted photons.
Yes,
So is it
you can do. So, if you put a single atom in a cavity, if you are in a strong coupling regime, you don't even have to have a multi-level atom. It can be just a 2-level atom. You can emit multiple photons instead of one by driving highly excited couple states. I've done that in the past during my postdoc. You can emit pairs of photons instead of one. We haven't done this here. Whether that would work or not, probably yes, but we haven't looked at it. You have to drive your system a bit stronger, and then you fairly easily get limited by these blockade effects then. It's probably works, but for single atoms, I completely agree with you that works too.
A nice question. If you go to that photon population versus time graph, I think just the slide graph. So,
To the photon population,
yeah, this one.
Yeah.
Let's say. So just if we do a cavity ring down spectroscopy,
mhm.
and then I would have a photon population as a function of time
Yeah.
graph as well.
Yep.
And then if I subtract that, then is it fair to say that the effect you are modeling is that, or that's naive way of thinking?
So when you're speaking of cavity ring down spectroscopy, okay, cavity ring down spectroscopy, what I know of it is you have a cavity that you prepare in a steady state, you switch off the driving and you look at your light decaying. I don't expect anything special to appear. If I just switch off everything, I'm gonna see the natural decay lifetime of my system. That's not what we see here.
Of course,
No,
I
no.
understand, but there will be some contribution to that as well, or not?
Not at these time scales. The cavity decay is much faster than these 2.6 microseconds. It's the cavity decay is like in, it's basically, yeah, it's going to be in 30 nanoseconds or so. Yeah.
So, one question. So in that population, I see a flat top at t goes to 0.
Yeah,
So can I study something like quantum CNO effect?
that's pretty much what happens here. Actually, you can look at it that way,
Okay.
in a sense.
Just
Yeah.
proceed.
Yeah, you can.
Okay, if not next time, Alex.
Thank you. All right, guys, I think we're almost all here. So let's get restarted for the second session of this morning. So I'm Alexei Rozumtsov. You've seen me too much already during this conference. Based in Paris, I'm here with David, who sits in the back. So if you have questions about what we do in the lab, maybe not the old science, but the things that we're doing now, you can go ask him. So now we're gonna have tutorial on dipolar Bose-gas Bose-Einstein condensates by Rajesh Nath from the ISR in Pune. Thank you.
Yeah.
Floor is yours.
Thank you for the introduction. And also, thanks for inviting me here, Sanjukta, and all other organizers. So I have a collaboration with Sanjukta on Rydberg atoms, but unfortunately this is not the Rydberg atoms, it's a dipolar gas, and also Saptarishi we have the NQM at RRI, so it's I'm coming more often than. This talk I will talk about droplets and supersolids. I don't know if how many are familiar with these topics. So the aim of the, so I was initially a bit confused what was tutorial means. Even I asked, do I have to prepare an assignment or something like that? Because in our ISR Pune there is a tutorial section for every lecture. Okay, so we give assignments. So the whole idea of the talk is to introduce you droplets and supersolid, and just tell you what exactly droplet and what is the mechanisms which leads to droplet, and also the supersolids. The supersolids are seen in different kind of Bose-Einstein condensates like spin orbit coupled BCs and so on, cavities, BC in if you place it in a cavity, and this is particularly for dipolar condensates. Okay. So I mean, this is the typical picture. It's all started from here, 2016 from Stuttgart, from Tillman-Favre group actually. So then the whole story of the dipolar condensates is rewritten in the sense that the people thought what is the dipolar condensate is not exactly same as what it's been after 2016. Okay. And the reason is because of the droplets and eventually the observation of the supersolid, which has been in the market theoretically for a long time, and finally when it came from many different directions, and it becomes very abundant now to prove the properties actually. So this is, what you see here is a top view of this guy from the top view, and actually it's like a filament. The reason the filaments is because of the attractive dipolar interaction, which is anisotropic. And so we will understand how these droplets, and it's not a periodically arranged way here, it's just a kind of gas of droplets. But if you can properly put it in a harmonic confinement, they can organize into a crystal kind of with some coherence between the droplets. And that's what you call as the supersolid. Okay. So we'll start from the dipolar potential. So when I talk about dipoles, it's polarized with a strong external magnetic field in the case of magnetic dipoles, but it can be electric dipoles. For instance, the polar molecules, the dipole is electric in nature and quite very high compared to the magnetic moments of atomic species, because the atomic species, the magnetic moment come from the number of valence electrons, and which is a few Bohr magnetrons, like 6 to 10 typically for the chromium to dysprosium. But in the polar molecules, it can be few dBs, like 1 to 4 dBs, and which you can, I mean, exactly not the conversion in unit, but 1 dB can be seen as like 100 mu B equivalent to, okay. So the strong, the electric dipole interaction can be quite heavy compared to the magnetic part. So if you have a polarized dipoles, let's say along the some direction, which is typically we take as Z direction, then the dipolar potential is this symbol form. And the property of this dipolar interaction is this 1 by RQ, which is, we consider as a long range interaction in the cold atomic systems. And the other important part is this theta part, which gives you an anisotropic character. So what does it mean is, so if you have two atoms which dipoles oriented parallel, then they repel each other. But if they are on top of each other, they attract actually. Okay, this is very crucial, because if you know that in 2D or 3D Bose gas, if I have attractive interactions, then they are very susceptible to something called collapse instability. So eventually you lose atoms and the BC get destroyed. So that means this attractive interaction makes the stability properties of dipolar BC a little bit tricky business. Okay, So you may better use your trap, confine in this attractive part and try to stabilize this guy. Okay. So the interplay between trap and the dipolar orientation is a bit tricky in dipolar BC, but in usual contact interacting BC, you will see that it's not that tricky actually, unless you drive these S-wave scattering length to negative values. Okay. So the story, I said that the experiment which happened in 2016 in Stuttgart, which changed the course of dipolar BC. And the reason is, I mean, if I look at it, so before it was a chromium BC, before the dysprosium and erbium which came into picture. And most of the physics is well described by the so-called the Gross-Petrovsky equation. And this is the first time in this, which I wrote in this form, in a Hamiltonian form actually. So this is the kinetic energy. And this is basically the harmonic trapping frequency along all three directions. And typically you have the van der Waals interaction, this contact potential. And in addition, I have this dipole potential here, okay? And this is the long range and anisotropic potential which come into the Bose gas. So up to 2016, the physics was well described by this Gross-Petrovsky equation, excellent agreement with the experiments and so on. But the Tillman experiment, which didn't match anything to what it is predicted by this guy, okay? And we will see how it changed. So after 2016, I would say chromium is still, you can use this, there is no problem. But as soon as you come to erbium, dysprosium, and molecular BCs, so you have to take into account an extra term in the, this is so-called the beyond mean field correction, now we call it as, it's a famous LHY correction actually, okay? And one has to take into account this, incorporate this H, and then do the calculations, and this will agree with the weak to moderate, I mean reasonably strong dipolar interactions. So if you really go to very strongly correlated region, of course this will break down because, okay, so there are problems actually, okay. But okay, so at least now the people are happy with the dipolar BEC and with this so-called extended Gross-Petrovsky equation because it is extended from the previous nonlinear Schrodinger equation actually, okay. So my talk is all about these two guys. So I will tell you what was the problem here, and then I explain how this guy kind of solved this problem. So as I said, this was this guy, and in experiments you can tune this harmonic potential. Basically what you can do is you can play with the aspect ratio of the harmonic trap. If you take a radially symmetric potential, and if the radial frequency is much larger than the axial trap, you get a cigar kind of condensates. And if you do this on the other limit, you will get a pancake type of Bose gas, okay? And as I said before, the geometry is pretty important for the dipolar gas because of the anisotropic nature. And the other important thing in all this experiment is called atoms is high controllability. So the interactions are not quite arbitrary. It can be precisely controlled. For instance, the S-wave scattering length can be tuned using the Feshbach resonance. It's basically you just couple the free states to a bound state of another angular momentum channel. Thereby you can tune the S-wave scattering length, okay? And you can go from minus the attractive nonlinear interaction to the repulsive nonlinear interaction. This was quite important for people who study bright solitons and so on. So you can drive the scattering length to negatives and see self-bound bright solitons. And this also can be tuned using optical Feshbach resonance where you actually couple to a highly excited bound states actually. Okay, so these are advantages and disadvantages, but in principle there is a high playground to tune these interactions. And if you come to dipolar interaction, also it is tunable. You can use rotating dipole field, magnetic fields and effectively change the way it interacts. It has been experimentally demonstrated also. So as I said that if the dipoles are like this, they attract, and they are like this, they repel. But if you place it in a rotating field and carefully choose the parameters, and you can see that they will repel here and attract here, okay? So why it is important, this will give you a completely different physics, and also you can see that now the attraction is in a plane. Before the attraction was along this direction, but now it's in a plane actually. So You can play with all of these things actually, okay. So of course this leads to a different kind of physics actually. Yeah. So that is not the only possibility. Suppose if I have a pancake, so I just suppress the motion along the axial direction, and I can now tilt the dipole so that I can change the anisotropy in the plane, within the plane. Before I was talking about the dipoles are like this, so it attract and it repel, okay. So it's kind of three-dimensional picture. But now I put everything in a plane, and now you see that by tilting, so if alpha equal to 0, all are polarized along perpendicular to the plane, so they repel each other in the xy plane. But if I put on the plane in one direction, so it is attractive along that direction and repels along. So it's changed from a purely repulsive gas to a partially attractive. So you may wonder why these are important, because the property of these Bose gases is crucially depend on whether it is attractive or repulsive actually, okay. And more importantly, it's not just, okay, the quasi 2D regime, typically the dipolar interaction can be kind of short range, but still you will see long range effect in the system, okay. So other important thing in this, the Bose-Einstein condensate is like you have a condensate and you look at the surface excitations. Basically, these are the low-lying excitations on the top of the mean field, which is a condensate wave function. And this can be explicitly calculated, and this is so-called the famous Bogulev excitations on top of this. You can see like a standing waves on the surface of the condensate with a small amplitude oscillations on the density. So this dispersion is provided by this, this Ek is just a kinetic energy term here, and the G is the contact interaction. So this is particularly for the non-dipolar case, okay. And if you look at this, this has been exactly measured. It is an excellent agreement with the experiment. So this has been exactly, these are the dots are the experimental results, and this solid line is actually this guy, and this dashed line is the free particle case where the G equal to 0. So it's purely a quadratic dispersion. But in the presence of interaction, you will get this phonon branch, which is the linear dispersion, which is the speed of the phonon is provided by the square root of the interaction strength, okay. But in the large scale limit, of course, the interaction is not relevant. It becomes like a free particle, okay. So in the low energy excitations are the linear phononic branch. And this is important because, for instance, if you tune the interaction, G is proportional to the S-wave scattering length, to an attractive using the Feshbach resonance, this root G becomes imaginary. So that means the modes become unstable, and these modes can grow exponentially on the condensate surface, and that eventually leads to the collapse and the destruction of the condensate. So the phonon instability, which means the G is negative, leads to the collapse of the condensate, destruction of the condensate actually, okay. So then you don't want that. But in 1D it's a tricky business. 1D even the phonon instability leads to stable bright solitons. So there is no collapse in 1D. So the collapse is actually in 2D and 3D, okay. But now the different story is, as soon as I put the dipolar interaction, it's not just 2GN, there is this additional momentum dependence which come from the dipolar interaction because of the long range nature of the dipolar interaction. The contact is just contact potential, okay. So it is independent of momentum. So, but the Fourier transform of the contact potential is independent of momentum, but the Fourier transform of the dipole potential give this additional momentum dependence. Then of course, then you would expect that the linear and the free particle kind of dispersion may get modified, and exactly that's what you see here. And what we do here was we also tilt the dipoles in the plane so that there is an effective anisotropic interactions in the plane. So on one direction, the ky direction, you see a minimum in the spectrum, which conventionally it is called the roton because of the helium spectrum, okay. And in the other side, you will get the typical linear free particle branch behavior, and this will be the roton minimum. So now in the dipolar BEC, so we have going from the short range condensate to dipolar, you have there is a new kind of excitation emerges, which is the roton, and this maximum which we call the maxon for the reasons actually. Okay. So what you can do is now you can control the S-wave scattering length and make the previously I said if I go G to negative, the phonon get unstable, and similarly I can tune this minimum go down the energy line to become imaginary, and this is people call it as the roton instability. Okay. So in dipolar VC now there are two kinds of instability. So in the short range there was only one, which is the phonon instability, which is the long wavelength excitations becomes imaginary and that exponentially grows. But in the dipolar VC I have a finite moment instability, and this would expect a kind of different physics, and people know that the roton instability can in principle lead to supersolid, okay, because it provides a finite lattice on top of the condensate, some density finite modulations actually. That was the key idea. But you see that this attractive interaction is a bit tricky, because as soon as the density modulations grow, the attractive part try to overtake everything, and they try to put more atoms and more atoms and more atoms on top of each other and collapse the system. Okay. So the purely dipolar gas, even though the roton instability one would expect, so you can, what you can expect, then you can see a transient supersolid like behavior, which doesn't last long enough because the collapse will eventually overtake it. So that's what exactly you see. So you can study the dipolar BC in a 2D. Here for the simulation we take a homogeneous condensate so that it is easy to analyze and see because the spectrum is calculated for a uniform density. And the phonon you need a slightly larger box because the long wavelength excitations, and the roton instability which is happening at a finite momentum. You can see there is a slightly different. The reason why it is here slightly different is because the low moment instability involves there is a flat multiple modes actually. But in roton instability you can pinpoint this minimum, and that gives you a very nice stripe pattern actually. Okay. But as I said, these patterns are quite transient because of the attractive dipolar interaction. So this is based on purely the Schrodinger equation.
Sorry, just one question. I think I missed because originally X and Y are completely symmetric. So you broke the symmetry
By tilting the dipoles.
You tilt only on one direction, but you could tilt the other one, but you choose
To tilt on one direction actually. Okay, so you tilt along the x-axis actually. Okay, so that gives you the stripes. This is all using the 2016 before the normal, the first Schrodinger equation, okay, the Gross-Peters scheme. So recently, just the end of the last year, they did exactly the same experiment, and they stabilized they saw a stable stripe pattern just because of the delta mu, which I have to incorporate, which is the LHY correction. So when you incorporate that LHY correction, the collapse is prevented, and that will be stabilized into a nice supersolid. Supersolid means on the superfluid background you have a very periodic density modulation. Okay, but the celebrated supersolid is slightly different, which is an array of droplets, and the coherence is between the droplet is maintained by a weak superfluid background. Okay, so there are two kinds of supersolid now. The one you talk here is a bulk BEC, and on top of it there is a weak density modulation, and that weak density modulation is stabilized. Okay, and then the coherence, the question of coherence between the density peaks is trivial here because it's a weak modulation, but in the droplet it's a non-trivial question because you need a flow of particles between the droplets to maintain the coherence between the droplets actually. Okay. So you have to keep in mind that there are two kinds of supersolids in dipolar piece. So we haven't come to the droplet supersolids actually. Okay. So weak roton instability you can stabilize into a striped supersolid with a weak density modulation, and the stabilization mechanism I haven't said, that is given by the LHY correction. If I don't incorporate the LHY correction, this pattern is transient and it will collapse. Okay. Okay, now let's go to the Tillman-Fauss experiment and put the LHY correction. Okay, so this was the experiment. Actually, when they did this experiment, erbium, they were expecting a collapse. They just reduced the S-wave scattering length, which is repulsive in character, and they want to make the attractive part of the dipolar interaction dominating such that the system collapse. And when they did the same experiment with the chromium in a spherically symmetric trap, they saw very nice, beautiful D-wave collapse because the dipolar interaction has that D-wave symmetry. So that is the trademark picture of dipolar BC for a long time. And they tried to see this in this experiment, but unfortunately, this was more on a pancake, kind of pancake, but not 2D pancake, but really 3D condensate. But they didn't see that D-wave collapse or anything. They just see it's like some kind of density things which is floating around for a long time. Okay, so these are the pictures of that from the top of this. If you look at here, it is actually a filaments of dipolar BC stabilized by the LHY correction. And the filament is because the dipole is oriented along the Z axis. That gives me this elongated condensate. You can think like an elongated condensate, but there are very key difference from the condensate regime and the droplet regime. There I will just comment about few of these things. Okay.
Sorry, what are from there are several pictures. What changes from them?
I think it's at different times they plotted it actually to show that it survived for sufficiently long time actually. Okay. So collapse is like you will lose everything like in a boom. The number will deplete very fast and it's gone actually. Okay. And so it is a stabilization at, so what happens is the system is trying to collapse and collapse and the density increases locally. And in the chromium BC what happened was nothing prevented this. It just collapsed and it just shrink. So what happened is in dipolar BC the collapse is slightly peculiar. In normal condensate, in the short range case, the collapse is happening from all three directions. Okay, but in dipolar BC, the collapse is happening from the plane perpendicular to the dipolar orientation. So you will get an elongation of condensate. The particle around this dipolar axis will shrink radially. So you can assume that radially the kinetic energy is increasing because of the uncertainty principle. And the particles are more elongated along the Z-axis. At some point, the quantum pressure is too large that it boom, eject electron. But the ejected electron is radially ejected, but then there is an attractive interaction from the axial direction. So the atoms are doing like this, and this it's from here also. So what you can see is that there is a kind of nodal plane at the center of the condensate, which leads to a formation of something called the vortex ring. Okay, so the angular moment is actually created by the dipolar interaction itself. Eject and the attractive part will pull, and then it comes here and it comes here, and then in the plane perpendicular to the dipolar axis you see a very nice vortex ring. And that has been the experiment in the chromium, which is a transient feature. Okay, and but this is completely different. And mean field theory, if you do the simulation mean field theory, you should see what they see for the chromium. It didn't. The numerics and the experiment is not matching at all. And then what is the problem? So the first, this nature paper came without explanation. They just see that the Rosenberg instability, because this is a ferrofluid, you have kind of roton instability and you see the spikes on the surface of the ferrofluid, and exactly that is that experiment. So this is called the Rosenberg instability in a dipolar condensate, which is act like a ferrofluid. But of course, after this, there are so many theoretical papers came. The people introduces the three-body collisions, three-body interaction, and that also prevented the collapse because the scaling is different from the scaling of the two-body interaction. So the three-body can prevent the collapse. Actually, it's not surprising, but they thought that the three-body interaction coming into picture because of the high density of these guys. But actually then the reason happened to be the correction from the LHY, the quantum fluctuations. Quantum fluctuations means you have the condensate at k equal to 0 get virtually populated to the Bogolev modes, which k not equal to 0, and that lead to a perturbative correction to the ground state energy, and that become density dependent, just like the three-body interaction. And that density dependent, that power is crucial, that prevents the collapse. Okay. Because you see that the energy, the interaction energy is proportional to density square, and the correction should be greater than that power. Okay, and that happened to be that power greater than, because the attractive part is going as n square. So I need a repulsive which is going above n square to prevent that collapse. And that is actually provided by this first order correction to the my ground state energy, which is a virtual coupling to the Broglie modes, which goes like 2.5 to 2.5. Okay, but that 2.5 will come into picture only if the density is sufficiently high, and that makes this guy stable. So, and you see that this density n is here. This is the chemical potential. It is 3/2, but the energy which will be dou mu by, I mean dou n, then it will go like n. The energy will go like dou E by dou n equal to mu, and then E will go like n power 5/2. Okay. So the interplay between mean field interactions, the pure mean field interaction, the system will collapse. You lose the condensate in very short period of time. And then as soon as you include this delta mu into the Gross-Petrovsky equation, the condensate collapse is prevented just because of the scaling which is sitting here. N power 3/2 for the chemical potential, but when I put it on the energy, it will be 5/2, okay, which is 2.5. So then you have a stable high density droplet, which is typically 1 order, 2 order magnitude higher than the typical BEC density. Okay. And of course, the people in Innsbruck studied also the Roton spectrum, which is the finite moment instability, which I said before. And they see the stable density modulated BEC also. And then there was a series of paper which came that since you have a droplet, why can't we, because the initial experiment which was, there was no coherence between the droplets actually. So it became highly incoherent after some point actually. So it's not a super solid actually, it's just a incoherent gas of droplets. So what they did was they put a kind of radial, cigar kind of condensate, and we drive the system into the droplet regime. So then you form a line of droplets, and then if you are not deep in the this droplet regime, there is a slight overlap between the droplets, and you can establish a nice coherence between the droplet, and that the people saw it as the super solid. Yeah.
Can I ask, on the previous slide, I'm confused because you had an integration over your dipole-dipole. Doesn't it diverge?
No, this doesn't. Actually, this is a good question actually. This has been taken care and finally we get into this form actually. So if you want to understand, the LHY correction is like a summation over all the 0-point energy fluctuations of each of the Broglie mode that would diverge actually. Okay, so that has been taken care and this won't diverge actually. Yeah. Right, yeah. So this is the one I was saying. So you take a cigar condensate, go to the droplet regime, and if it is 94A0, you are not very deep in the droplet regime. If the droplets are there, then there is a superfluid background which provides the coherence between the droplets, and you have a super solid. But if you go slightly deep in the droplet regime by lowering the S-wave scattering length, then you get an insulating array of droplets, which is the crystal of droplets actually. But in the experiments, you don't prepare like that. You create a BAC and adiabatically try to, as slow as possible, quench the S-wave scattering length. And in principle, of course, it's not as nice, but you can see the signature of BEC and insulating array of droplets actually. Okay. So all of these things, in principle, I summarize it here actually with all the different mean field regime and beyond mean field regime. And how much time I have? So recently, very recently, there had been a new kind of setup which is emerging, which is called doubly dipolar atoms. So it's on the same dysprosium atoms. Dysprosium atoms are magnetic in nature because of the 10 valence electrons it has. But the interesting thing about the dysprosium is, I will just, so the doubly, so that means I have two competing dipolar interactions actually. I will tell you how this comes. So there is a very recent experiment in Berlin. So they measured electric dipole moment in a magnetic atom. So that means there is a competing dipolar interaction. And this is the magnetic interaction and this is the dipolar interaction. This would Of course, this is highly complicated because you can have highly non-trivial anisotropic surfaces. And for instance, if I just go, this is the typical one we were just talking about so far. There is an attractive part along the Z axis and radially repulsive. And if I can control the angle between the electric and magnetic dipole moment, I can completely tune these properties of the anisotropic properties of these potential surfaces. So that means the condensate may get into something non-trivial objects actually, shapes. I mean, it's kind of engineering the density of the condensates, okay. So in principle, you can play around and interplay between the relative strength of the electric and magnetic dipole moment as well as the orientation of the dipoles. So there is a full playground is open to create these non-trivial anisotropic patterns. Of course, the consequence of this BEC is still not experimentally they have able to measure this in the dysprosium. Okay, the whole idea started from the France. Okay, so they found that it is possible to generate an electric dipole moment in a dysprosium. It's very peculiar to dysprosium. The reason was they have a quasi-degenerate states with opposite parity, and one is a metastable state, long lifetime. So what you have to do is you just weakly admix with the electric field, and that will create the electric dipole moment along the direction of the electric field. And then you can independently control that electric dipole moment and also the magnetic dipole moment, which I said so far. So this gives you an interplay between both the electric and magnetic dipole moment. Okay. So these are the details. You can find all the details in this theoretical paper. Yeah. And then, so this was the experimental paper, which is also appeared 2025 November. So they were able to exactly measure. This is not in the cold regime, but all they did here was to show that indeed the calculations done in the previous theoretical paper is exactly matching with the experimental. So these are not in the BEC regime, but they were able to demonstrate that in dysprosium atom it is possible to have both electric and magnetic dipole moment. It's very unique actually. Okay. And based on that, we put up the doubly dipolar Bose-Einstein condensates. We thought, okay, let's put it like that. And why it is interesting, so we noticed that the dipolar potential, which is attractive along one direction, can now be tuned to attractive in a plane, just like this. Okay, so that means the droplet now, which is cigar at alpha, this when both dipoles are along the one direction, it is cigar. It is the typical droplet which you see in the Stuttgart experiments. Now can be like a pancake. Okay, so the key point is here. I just tell in advance that typically this structural transformation is done in cold atom experiments by controlling the trapping potential. So you take a cigar, as I said in the very beginning, you change the aspect ratio of the trap, you go from a cigar condensate to pancake. And here you see that it's purely driven by interactions. Okay, and so in one side I have a cigar shaped droplets, and I make these two dipoles perpendicular to each other, and then I will get a pancake droplet. And we look at the properties of these gases, and we found that it's actually behaving like a strictly 1D object and a 2D object. So actually there is a dimensional crossover purely driven by interactions, not by trap. Okay, this is a very unique scenario in condensate physics, because all the time when they use low dimensional condensate, it is purely by engineering the external potential, which is a trap. But here it is driven by the interactions itself. Okay. So this is a full phase diagram. Okay, of course it's not explored completely, but in one particular region we explored where we want to see the thing actually. So we also looked at the thermodynamic properties using the PMC calculations, and we found that the transition temperature in the BEC regime is much lower temperature compared to the droplet regime, just to see that the droplets are much more robust to thermal fluctuations. Actually, that is one of the main results here. So this is my last part actually. I will quickly cover, and you can see that I already said that it is possible to have an array of cigar droplets, and the coherence can be built. And this gives me an array of 1D droplet, supersolid. This was the typical experimental scenario. And now we looked at this in the case of doubly dipolar BEC. there is a new kind of droplet emerge, which is pancake. Then we thought, of course, there should be new possibilities. Of course, this is same as the Stuttgart experiment or other people who do the experiment with normal BEC. This is the superfluid background, and the droplets are made coherent with the superfluid background. Okay, it's the usual scenario. Of course, I saw some additional structures in the W dipole. I just skipped this for the moment, actually. So in principle here, you got an opportunity to completely change the morphology of the droplet, which was not possible in a, unless you try some external potential, actually. Okay, here it's just purely an interplay of the interactions. Okay. So, okay, so I just switch the, okay, so this is, I just don't want to go to the technical details. So this is the new kind of supersolid could be possible in the doubly dipolar BC, which is an array of pancake droplets, actually. Okay. Okay, so with this, I hope I have conveyed that what is droplets and what are the two kind of supersolid which can be observed in the dipolar condensates. And of course, you can also have incoherent array of pancake droplets, and I think I will just stop here, actually. Okay. Thank you very much. Yeah.
Okay. So if you go back to the previous slide, see you have a magnetic field and an electric field which are not aligned. So in such a system, when you put an atom in a kind of cross electric magnetic field, you get alignment orientation effect, which is a dynamic thing where you basically quantizes on the magnetic axis, electric axis, and so on and so forth. So what is how does that dynamic play into the droplet mechanism?
That we haven't looked at, because this is strictly assuming that there is a spin polarized magnetic state. Okay, so and then which is weakly coupled to the the opposite parity. There is a weak population. Okay, and that is significant enough to get the dipolar interaction which is required for the other electric dipolar interaction. So these are weakly interacting gas. Okay, so you have a magnetic field which polarizes you spin polarize the gas, and then you weakly admix it. It's not like exciting completely into the.
No, it's not about. See, if you just take a neutral atom and you put it in cross electric and magnetic fields.
Okay.
Okay. What you find, see, the MJ is not a good quantum number for electric field. It's a good quantum number for magnetic fields.
Exactly.
So you get into this competition driven by the quantization axis choice between electric and magnetic fields.
Exactly.
So, and that, if you look at it, these are papers from the 70s.
No. What I'm saying is that additional contribution. So let's say define MJ prime. Okay. So the initially MJ is equal to, let's say, minus 10. Okay. And this MJ minus 10 plus this additional contribution is very small for this case. So this has to work in that strict sense. Okay. Okay. It's not like I'm just going completely away from this initial quantization thing. There's a weak population, MJ minus 10 plus some weak.
So in this particular formalism, you're ignoring the fact that there's a dynamic at the
No, there is nothing. Exactly.
Okay, fine, thanks.
We had one question here. Yes, thank you for your talk. And I was wondering that in the case of the experiment, have you or any group observed pancake shapes?
No, actually, even the experiment which I taught 2025 this November, it's in a thermal cloud, but they were able to show that the both dipole moment. So the experiments, as far as I know, it's only in Berlin, this group, and there is an effort in Innsbruck.
Okay.
Okay.
And you showed that there could be two possible cases of pancakes, either coherent and incoherent, if I remember correctly. So how do we go from one to the other?
You just simply reduce the scattering length in this case.
Okay.
Okay, just simply going to deep in the droplet region.
And imagine that we obtain pancake droplets. How do you observe this? How do you
single
verify?
pancake. So what you can do is because these are this droplet are self-bound also. So for this one single droplet, I don't need a trap. For super solid, I need, because what you do is you take a big, for instance, if I take a single droplet, okay, just like this, and how do they create super solid is just confining strongly in that direction, and that cost of energy breaks this droplet into 2, 3, 4, okay, and then they form a coherent object. So as far as the single droplet is concerned, it's a self-bound droplet. Okay, so that how you obtain is like you just look at the size in time. It doesn't change. It's stable.
Okay. Thank you so much.
Yeah.
Are there further questions anywhere? Okay, I don't see any. Oh, one there in the back.
Thank you. Thank you. It was super interesting. From what I know on super solid, I've always heard that you need 2 spontaneous symmetry breaking.
Exactly.
And is this mechanism of forming coherent droplets can be thought as a symmetry breaking in the
Exactly, it's a good question. So the question is like, so you have both the U1 symmetry breaking, which tells you that there is a superfluid, and then there is this translational symmetry breaking, which is the solid crystal. So when they did this excitation spectrum, the signature is seen in the excitation spectrum. So there is a new Goldstone mode which arises because of this, and this has been demonstrated in for a few years ago actually. Yeah.
Okay.
Yeah, it has been seen.
Okay, thank you.
Okay, now I think we have to stop. Let's thank the speaker again and move to the next talk. Which is going to be given by Divyendra Roy, who's working here, who's going to be speaking about speed noise spectroscopy of periodically driven alkali vapors.
I wish we can do this experiment sometimes. It's really
Sorry.
Yeah. Can you put it here? Because I'm having little difficulty. Thank you. So when we are starting? We are starting 12 to... Okay, thank you. So let me begin thanking the organizer, particularly Sanjukta and Saptarshi. So I am going to talk about spin noise spectroscopy of periodically driven alkali vapors, RF versus optical driving. This work has been done in collaboration with Saptarshi Chaudhury's group, and so please stop me in between if you have questions. So spin noise spectroscopy is a measurement technique to measure spin dynamics in atomic systems or semiconductor heterostructure non-perturbatively. So we really don't want to disturb the system much and still try to get the spin dynamics inside the sample, which can be even in equilibrium because of thermal fluctuation or quantum fluctuation in ultra-cold atoms. And this technique can help one to probe such dynamics. Here mostly I will talk about in thermal atomic vapors. So here is a brief outline of my presentation. So I will start by introducing spin noise spectroscopy of atoms. So this will be relatively simple. Then I will discuss something which was done in Scott Crooker group long back when I was postdoc there. So this is spin noise spectroscopy with radio frequency field-driven atomic vapors. And then I will talk about what Saptarshi and Sanjukta they have done. So spin noise spectroscopy with 2 optical fields-driven atomic vapors and ultra-cold atoms, which I will not talk, but maybe Saptarshi will little bit talk about. Okay, so as I said, this work which I am going to present in collaboration with Professor Saptarshi Chaudhury's group at RRI or LAMP and Scott Crooker's group from Los Alamos National Laboratory. Okay, so I hope everyone knows about Faraday rotation. So this is a magneto-optical effect which Michael Faraday discovered to prove that light and magnetic fields are related. So what is Faraday rotation? So when a linearly polarized light passes through a transparent solid or liquid of length L in the presence of a magnetic field B along the light propagation direction, so then this plane of polarization gets rotated by angle theta, and that theta generally proportional to the external magnetic field B and the length of the sample L, and the proportionally constant is given by Verdet constant. So this is an empirical formula which, like Verdet proposed, for the Faraday rotation of linearly polarized light in the absence of any absorption. So this is mostly dispersive medium. Now, this can be understood even from simple consideration that is linearly polarized light can be thought as superposition of left and right circularly polarized light, and when you have external magnetic field, left and right circularly polarized light sees different refractive index. So because the birefringence of the medium, you get this Faraday rotation, which now you can write as difference of this refractive index for left and right circularly polarized light. And a simple way to explain that how birefringence emerge in atomic medium is just to think about the simple atomic structure. So here I am showing energy diagrams for two hyperfine levels. So my ground hyperfine levels F consist of 3 MF levels +1, 0 and -1, and excited hyperfine levels F prime maybe with just MF prime equal to 0. So here if I again sign this linearly polarized light and decompose it into two sigma plus and sigma minus light, one can see that there will be this coupling of light from +1 to 0 or -1 to 0. But when you have equal population here and that these two transitions are degenerate, you do not have any Faraday rotation. But this can be changed by applying an external magnetic field along the direction of light propagation, and that external magnetic field will break the degeneracy of sigma plus and sigma minus transition, and because this degeneracy is broken, now the refractive index for sigma plus, for example, will be different from sigma minus this one. So this leads to this birefringence in the atomic medium or Faraday rotation, but this requires magnetic field to break the degeneracy, but one can also see without applying any external magnetic field, such things can happen. So in the absence of magnetic field, if you have population imbalance in the ground manifold, for example here, which can be created by maybe optical pumping, so then you will have effective difference or a relative difference in the population, which will create relative difference in the refractive index. So in principle, I can now say the relative difference of refractive index for left and right circularly polarized light is proportional to the number of, let's call, up atoms minus down spins in this atomic configuration. So what I want to say then, the Faraday rotation is proportional to some spin polarization along the light propagation direction, and that spin polarization leads to Faraday rotation, and that will be like depending on, of course, some lag. So the spin polarization at that time is related to Faraday rotation at that time, and one can then probe the spin dynamics, which I said the goal of this spin noise spectroscopy, by measuring Faraday rotation Faraday rotation. But now let's take, we have a paramagnetic samples in thermal equilibrium, and we have not applied any external magnetic field along the light propagation direction. So then we do not have any spin polarization. So on average spin polarization is 0, but still we can have, even in equilibrium, the spin fluctuations, and that will be non-zero even in such samples. And the goal of spin noise spectroscopy mostly to probe, or original goal was to probe such spin dynamics by measuring this Faraday rotation fluctuation dynamics. And the goal was another way motivated by this fluctuation dissipation relation, because fluctuation dissipation relation connects the fluctuations or equilibrium fluctuation with linear response coefficient. So by measuring such fluctuation, one will be able to measure susceptibility, for example, in such medium. So this, as I said, has been done already for electron or hole spins in semiconductor heterostructures, in atomic vapors. So my today's talk are mostly for atomic vapors. So as I was trying to say that we need to probe this Faraday rotation fluctuation. So what we do, let's take, we have a sample here, rubidium vapor cell, and we shine a light along the z direction, linearly polarized light along x-axis. And we have, this is the detection scheme which will measure the Faraday rotation fluctuation. So this consists of this half-wave plate, polarizing beam splitter, balanced photo detector, and spectrum analyzer. And if I measure this signal in this one, so we have, let's take, rubidium vapors in this system, and the shine light also is much detuned, maybe order of 10 gigahertz, 20 gigahertz from any atomic transition. So for example, if I have rubidium-87 atoms, so the probe laser is, in this one I am showing order of 8 gigahertz detuned from this D2 transition. So there will be very low any absorption of this probe laser or even excitation creation, and that makes these systems kind of non-perturbative or non-invasive. So in such experiment then, so which was first time done in Scott Crooker group again in Los Alamos, what they will measure, for example, in rubidium systems, they will measure like these two peaks. So this is done with an external magnetic field transverse to the direction of light propagation, and these peaks will emerge where these rubidium atoms, these 5s level, these spins in these Zeeman levels, they are fluctuating around. So there will be like del F equal to 0, del M F plus minus 1 transition in these Zeeman levels, and that transition of atomic electrons from this level to this or this one creates this peak. So this is the rubidium-87 gives this peak, and similarly if I have in that sample some amount of rubidium-85 isotope also, we'll see another peak. So this signal, which was originally measured in Scott Crooker group in 2004, so Saptoshi's group also could reproduce this experiment in RRI, or first time in India, and we have done not only, so these plots which I am showing from Moesher paper, which is in Saptoshi's group, they have realized. So not only will prove, like we have done this one in this paper, we have also tried to do optical pumping and try to measure those things. So I will not discuss those today. But what we really measure this one is the spin noise power spectrum, which is that quantity which I just said, the Faraday rotation fluctuation proportional to spin fluctuation in this sample in thermal equilibrium. So that in general one can write like it will be some Lorentzian type, and the Lorentzian, the peak, the Lorentzian is around omega naught frequency, which is because of this transverse external field, and the T2 is the kind of relaxation dynamics in these systems because of all different things you can think for relaxation of spins in such system. Now today I am going to talk about this alkali vapors, which will be periodically driven, and I am going to discuss about two kinds of periodic driving. One will be like with RF magnetic field, another will be optical driving. So I will try to explain what are the two schemes. So the first one is in the RF driving. So again I have this same setup, let's call rubidium-87 isotope. My probe laser is detuned from D2 transition. Now what I do, so there is an external magnetic field which is constant in this direction, but now I turn on another external magnetic field which is perpendicular to both x and z, so in y direction. But now this magnetic field is AC magnetic field, so like NMR experiment people do. So you will have now a DC field, you have an AC field which is in the RF domain, and this one will directly kind of couples to these different MF levels. So this is one setup which I will show you some data or experiment result and explain that what it helps to understand about the systems. And then in the other one, which is by two Raman beams, here apart from this probe laser, we shine two differently polarized laser lights which are now near resonant or on resonant between this f equal to 2 and f prime equal to 3. And this one we are calling this optical driving protocols, and the difference between these two protocols is that in this case, the second one, for example, we are connecting this F2 ground manifold, hyperfund manifold to the excited F prime manifold. So each of these ground Zeeman labels, they are coupled to this excited F prime labels through these two different polarized light, this red and green. So these F labels are not directly coupled, but through such a common bath. So you can think like I have two labels, F equal to MF equal to -2 and MF equal to -1. They are coupled to a common bath, which is MF prime equal to -1. And in general, when you couple the two systems which are themselves not talking but with a common bath, you will have effective imaginary coupling. So that will lead to some kind of IJ0 between different MF levels. In the case of RF, we have direct coupling through this RF field, but in this case we have kind of complex coupling between different MF levels. And that really changed the dynamics of these systems. So the first one, which was done, as I said, in Scott Cooker's group long back, 2014. Please.
So can you adiabatically eliminate upper?
Yeah, that is what actually required. Sorry, I should have told. So actually we are thinking that these MF prime populations are almost negligible, so, and we are that's why you get the IJ0. Okay, so in that RF driving scheme, which was done in Scott Cooker group back in 2014, so what they have done, I have already explained. So let's consider now, first in the absence of this AC field, only we have a DC field, and of course we are probing the spin resonances in such systems. So this is done with potassium-41 isotopes, and again in thermal vapor. Now in the presence of this external field DC, no AC now. So in the B plots, what I am showing, there are like A, B, C, D, these different spin resonances from F equal to 2, and similarly F equal to 1, you have this E and F resonances. So these two of them, like this B and F, are actually degenerate, and similarly C and E are also resonant. So because of these four different resonances, so the spin noise power spectrum will show 4 peaks with spectral frequency. So this was like the equilibrium equilibrium spin noise spectrum. Now we drive by AC field. So this the next plot which is showing. So what is happening? So again, this is spectral frequency, and this is now the AC field frequency. So as we bring this AC field near resonant to this, let's call the omega A. So omega is the resonant frequency of this A transition. So as we bring this omega AC near this omega A, we see this kind of what is called monotriplet behavior. But this monotriplet emerge in A, but also you can look that the B transitions are also splitted like this kind of Euler-Towns doublet. So by bringing my AC RF field on the A resonance, we see that we have monotriplet, magnetic monotriplet, as well as this Euler-Towns doublet has been created. And as you bring this AC field now on this one, you will see again monotriplet, but now 2 Euler-Towns triplet to nearby transitions. So what it's actually suggesting that each transitions which are sharing common levels, they get split. And that splitting tells you that what are the kind of energy diagram leading to such spectrum. So we can see the correlation between spin resonances. And that is what main things we try to kind of propose through such experiment, that we can probe what is the correlation between spin resonances, as well as we can probe the degeneracy of such spin resonances, which I'll skip now because I want to talk about optical. Now we change the scheme of this driving. Instead of like magnetic driving, we are now having optical driving, and which I have already explained, and I will now consider first a 3-level scheme rather than the full structure like which I was showing here. So just consider one red and green, so which forms a like 3-level structure. And this 3-level structure, we have like 2 Raman beams omega with Rabi frequency omega 1,3, the frequency of the driving omega S1, omega 2,3, and omega S2. And again, we have these setups to probe the spin dynamics. Here, this blue colors is our probe laser, which is far detuned, maybe 30 gigahertz detune in this case. And then we have these 2 Raman beams with different polarization, which is driving these systems. And kind of these systems, we can write these three-level systems in terms of this Hamiltonian, which is in the rotating frame. So here mu dagger, sigma dagger, and mu dagger, they are these three transition dipole allowed in these three-level systems. And with these things, we now are ready to probe again the spin dynamics of this vapor. We have done also in ultra-cold atoms, which I will not talk. So in the vapors, if we do these things, so now spin noise power spectrum will be roughly sum of two contributions. One is this equilibrium thermal noise contribution, which is present in the absence of driving, and then there will be another one which emerges because of the driving, which is this coherent peaks. I will show like how these two different contributions compete as we change the power driving strength. So the first one, again this thermal vapor undriven systems spin noise spectrum, which has again two different peaks depending on the population of rubidium-87 and 85 isotope. Now I do a moderate driving. So this one is a moderate driving by these Raman beams. So the Raman beams, this Rabi frequency omega 1323 is not so high. So in that case, we have the background, this peak is still there, which is like this one. So this is the thermal contribution. But now, depending on the detuning of these two Raman beams, we have different coherent peaks emerge. So these different peaks are the coherent peaks which I was showing from here, which depends on this detuning omega S2 minus omega S1, which is the detuning of the two Raman beams. So when the detuning exactly match with the Zeeman splitting between 1 and 2, that is where you get the highest peak. And when you detune from this Zeeman splitting, they actually fall. So this is the moderate driving, but now we increase the driving of the Raman beams, and then you will see like there is no more, you see the background thermal noise, you only see these coherent peaks, which are almost 5 orders larger than this thermal intrinsic noise, and you only see these peaks as you change the detuning of the two laser beams, and these peaks also we reproduced from theory, and their envelope also we reproduced from theory, so it matches quite nicely all the features we have checked that paper. Okay, now I come to the last part, which like we not only considered the three-level structure of this full energy level diagrams, but we will consider like all these coupled lambda structures. So in this one, what we have done, we have now this again ground hyperfine manifold and excited hyperfine manifolds are coupled by these two different polarization of Raman beams, and we have this, when we remove these 2, 4 and 6 or other excited levels in the adiabatic assumptions or the assumptions that they are actually almost negligible populated, so then we get this effective non-Hermitian coupling in the lower manifolds, and that leads to that a long coherence in such sample. So there is no coherence terms like this one. So this is the coherent contribution due to driving. There was no such contribution in the RF case, but in the case of optically driven system, this contribution emerged, and that contribution we believe mostly because of this maybe non-Hermitian nature of this coupling, and from that what we have been able to probe. So this is the experiment again in Saptarsi's lab. So we have been able to probe not only such huge peak, which we call fundamental peaks, which come from one photon transition between 1, 3 or between 3 to 5 or 5 to 7, like this is the fundamental peaks, but we see higher harmonics. And they come from higher order coherence, like 2 photon transition from 1 to 3 to 5, kind of that 1, 5 transitions, which will be at 2 of delta S. So the delta S is the, delta omega is the difference of two Raman beams detuning. Sorry. So then these peaks emerge at 2 of delta omega S, this emerge at 3 of delta omega S. So we detect such higher harmonics. For example, this is for Gauss manifold f equal to 3, so there are 7 levels in the Zeeman cases. So we expect 6 peaks, though we could only resolve 5 peaks. And we also tried to understand it theoretically in this paper, which Rupak, who is present here, developed such theory, and we can tried to see like, so this blue curves is our theory, blue and this magenta, or which color, red, are like this our theory and this is experiment. They don't really match nicely. There are other things which probably we could not incorporate here, but this is the things which I wanted to say. So now the summary and outlook. So we saw that there are coherent peaks which is there in the optically driven systems. No such coherent peaks is there in the RF driven system. We saw monotriplet or Latown's doublet or other kind of Rabi splitting for the RF driven systems. We did not see such things in the optically driven systems. So maybe a better experiment, a better theory which we are trying to do require to kind of understand all the differences or comparisons between these two. And also to just advertise one thing that this, again, Saptarsi's group, they have tried to use such higher harmonics to develop such kind of magnetometer. So these peaks, good precision detection of these peaks will be useful to detect or create magnetometer in such samples. With that I will finish. And this work has been done in theory collaboration with Rupak and my previous postdoc supervisor, Nikolai Sinitsyn. And then experiments are done with, in Saptarsi's group with two graduate student or PhD student, Moheshwar and Sairi, and in Scott group with Glassenup and Louis Young, with whom I have multiple papers also. So, and then others are Subhajit, Sanjukta, Saptarsi, Dhanalakshmi, Hema, and then Alex Breyer, Scott Cooker, and D.G. Rickel. So now I just want to say something because this conference is about so much nonlinear optics. I thought, actually I forgot to say that I worked in this field much more than even spin noise. So maybe I just say one things about this waveguide QED. So waveguide QED is about nonlinear quantum optics in open space without cavity, so in a cavity-free systems. So it's developed around 16, 17 years, and I have been working in this field from the inception. So I have developed many techniques to understand this nonlinear quantum optics with few atoms or multiple atoms, and this is probably one of the first review which on these topics, with of course offer a lot of papers I see you are showing. Actually, we did not call that time it's waveguide QED because of offer, because his experiments are not really waveguide, but we wanted to include both Rydberg as well as superconducting circuits. So Chris Wilson is an expert in superconducting circuits. So this is the review article. Okay, with that I'll thank.
Thank you. First question here.
I actually missed your last slide, last part, but it seems like you have hoppings are different in two different directions. Is that correct?
In this case?
Yes.
No, that's same, IJ0, but they create so this coherent dynamics, if we write kind of this Lindbergh equations or Heisenberg-Langevin equations, the coherent dynamics are coming from this IJ0, but it's really a non-Hermitian, so it's like when you take the Hamilton.
Non-Hermitian in terms of what?
Hopping. So you like in general you write IJ0 minus IJ0 if you write hopping between let's take 1 and 3, but in this case both are same sign. So I can write in the board if you wish.
It's okay. So I was wondering if it is possible to have something like the skin effect in this sort of.
Yeah. So actually we could not go to topology yet, right? So that required topology. So that we have not been able to. So maybe that's also something, theoretically at least we are thinking how to realize such.
So another related question. So I'm not familiar with this setup much, that's why I'm asking. So in this sort of system, so all you are doing, this is basically linear optics, right? Single particle optics.
In this case?
Yes.
Yeah, mostly you can say, but yeah, we are not in the nonlinear region.
So is there work on?
Yeah, so actually what I'm saying is some of the things that monotriplet or Latown's in this optically driven is required stronger driving, so that might reach, but surely not nonlinear optics region.
Has there been any work on this?
I don't know, and that's why I'm saying that one needs more experiment and theory both. Okay.
So in the context of cold atoms, one typically makes a very strong parallel between RF transitions and Raman transitions. And you seem to say that it's not the case, in particular with this complex coupling. And so I'm trying to understand where really the difference is.
So the complex coupling is emerging because of this, this kind of coupling, which is, you can think like I have two ground manifold here. They are not directly coupled by, in the case of RF, like direct coupling. In this case, they are coupled to a like excited levels, which I am considering as like, which de-excite very quickly, right? It's 2 gigahertz.
So essentially you perform adiabatic elimination, and then, but then still you're saying that it's not equivalent because of this I factor.
It's equivalent to like I have two systems coupled to a common bath. So like let's take I have two systems which they are not talking to each other, like he and me, and then connected to this environment which we both are sharing particles or energies. So then our effective coupling might become non-hermitian or complex, imaginary. So, okay, maybe I can explain it even. So I'm saying these excited levels here, they relax very fast, right?
Yeah, exactly. But when you perform adiabatic elimination, usually you would get rid of the bath and say that it's equivalent to having coupling between.
We start with our full bath even in the excited one, or the levels MF prime in the excited one, because that's through which we have this red and green green beams which are coupling these lower levels, right? So I have to put originally them in my calculation, and then I will do the adiabatic kind of adiabatic, or in some sense we are saying like this coherence D, let's call -2, -1 D, that coherence with time is not changing, and the coherence even in the green line between, let's take -1 and -1, that's also not changing. Is this part, that's the adiabaticity we are saying, like the ddt of, let's call, I call that transition, maybe I write because that's. So let's call these levels, I give a name, like each of the transitions as MF, let's call -1 and MF prime, MF -1 and MF prime, either I can write, in this case, -1. So this is, I am giving in transition dipole sigma, okay? I am saying like what we are writing in our equation, these are kind of 0. Okay, that's the adiabaticity. Is that part clear?
Yeah, right. And so what I'm not getting is that when I usually do that, then I say it's pretty much equivalent to having RF driving between the.
No, it's not, and that's what we are trying to claim. So that's a good point, that we are claiming that it's not, and that's why we see these peaks, which was not there in that RF case, and we want to understand where that even in RF case can. So these are all actually noise. These are all noise, and one can easily explain all these things through day state, which like monotriplet, other towns all works. Okay. So I guess.
I'll ask you more in person.
Yeah, I'd like to explain even further.
Other people. Wait. Wait a second. There was a question behind you first.
Thank you for your talk. I would be very interested to hear about.
I will be happy to explain also.
I was wondering.
So one thing, sorry, maybe I forgot to mention. In all of them, we are talking in thermal vapors, not when. Let's call not when these levels in ultra cold, so that the relaxation from lower to higher is different from higher to lower. So is that part clear? So maybe again, so in that, so these all the things we are talking in thermal vapor. So if these are MF levels, so we have relaxations. I guess there is a picture like that also. No picture. Yeah, maybe that one. So you see that gamma prime. We are taking this gamma prime from lower to higher Gman levels and higher to lower Gman levels same. That leads to thermal equilibrium or equal population of Gman state in thermal vapor. So that part is required. As soon as you break that symmetry, you will see different things. Okay,
Okay.
I can explain more. I mean,
And so my question was like when you do the optically driven excitation, we know that like the Klebsch-Gordon coefficients are not the same between the MF states. And how do you observe this in the spectrum?
Klebsch-Gordon coefficient we have not observed, but in this paper particularly we have looked like how different direction of quantization actually changes through this Klebsch-Gordon coefficient.
I would expect that the intensity of the spectrum
Might change.
Might change, but that's not the case?
Yeah, we tried to understand that. Like we tried to understand if we take like our light polarization direction as the quantization axis versus the external magnetic field as different quantization axis, what's the relation? We have something in that paper, but I don't think we can resolve Klebsch-Gordon coefficient.
Okay.
But that's something maybe.
Thank you.
He has one question further.
I'll ask maybe later. I cannot. So what I think when you have very intense pulses, for example, in the nonlinear regime, it seems that d sigma dt will it remain zero or it might not be, right?
Yeah,
so my question is whether this adiabatic elimination,
of the
this
excited
idea in the
states.
linear case, whether it will hold in the nonlinear case or not.
Yeah, I do not know right now.
That do I. This just came in my mind.
Yeah, I don't know right now. But one thing, as I was discussing, this gamma is very large compared to the time scale of our. So gamma is like 2
if the
gigahertz.
nonlinear strength is very small, then maybe
Nothing will happen. So you have to probably beat that one. That's probably very difficult.
Okay. By the way, there is exact photonic analog in waveguides. This system.
Oh really?
Yeah.
I'll be happy to know that once.
Yeah.
So RF versus optical, you are saying?
No. It's basically arrays of waveguides, and I can tell you.
Okay, yeah, very good. So.
I don't seem to see more questions unless I'm mistaken. If that's so, let's thank the speaker again and all speakers of this session. And let's head for lunch. Nadia, do you have something to say about when we resume? Because
one of the speakers is not here, but we do in Visio for Fabien. So we reconvene following the schedule, but we have a change of schedule this afternoon, for especially for the French people, because the participant from India who did not respond cannot go to the reception for the Bastille Day today. But the French people should be, I think, at main gate at 6:30 sharp, dressed up. So what we suggest is that we use the coffee break to go and change clothes. And try to start 5 minutes early with Umakant. So we will reconvene at 4:25, and we keep the last session on schedule. So a tutorial 45-minute talk, then the follow-up poster session, and the RRI visit is moved to Thursday. So all this is in the WhatsApp group with updates. Fabien wants to...
One precision, French people includes Indians from France, from all participants from France, including also Lebanese or German people, okay? Or Greek.
So it's the full delegation of 20 people, including Sanjukta. Okay, we hope it's clear. If it's not, come to us. Okay? Back here, following normal schedule at 2 o'clock, and we will have Fabien talking in the middle of the night in France. No, it's okay. No, actually, no, it's perfect for him. So we will have Fabien on Visio. He's following us live on YouTube. So actually, we joked about the cigars in pancakes. So a bit of French culture. We do a galette saucisse, so sausage with inside pancakes. So what you do is a multi saucisse quantum galette, whatever. Okay, enjoy lunch and interactions, and see you there at 2.
বাইরে আরো লোক আছে কিনা
I always say you Saptarshi, but your name is Saptarisi.
You realize now?
No, no, I know that, but I always like even in IISc, you don't say IISc, right? Two I is there. So similarly, I missed one I for him. Okay, so let's start the after lunch session with Professor Saptarisi Chaudhary's talk from lab. So Saptarisi is professor in light matter physics group of RRI, and he will be talking about quantum technologies with hot and cold atoms, forms and measurements. Okay.
Thanks, Dibyendu, for the introduction. First of all, let me thank the organizers for giving me this opportunity to talk here, and also the organizing team for smoothly organizing everything. Today is the second day, a post-lunch session. This is a bit unusual to see so many less people, because in a conference usually on the third day onward people number reduces, but I see that very few people are attending. Thanks those who are attending. Those who are not attending, also thanks to them. Okay, so I would say that I had given a very broad topic because I wanted to share with you some of the work what we do here in RRI, and also part of the Indian atomic physics experiments. So some pictures from my lab, some of them you will see if you visit the lab and during the talk also. So I will try to talk about a few topics. I will also introduce something which is highlighting India's own national quantum mission. So at RRI, we actually have a facility for atom and ion-based quantum technology development, and I will have a couple of slides for that also. So we are working on quantum computation with neutral rubidium atoms in optical tweezer array, a standard experimental setup here, mostly a technology platform. I will also talk about something which is very close to our group's heart. It's a cold atom gas mixture experiment. We work with sodium and potassium atoms simultaneously. And then Dibyendu gave a wonderful introduction to the spin noise. So we use it as a detection technique for both non-demolition imaging, which we are getting quite interested about now, as well as for quantum sensing, particularly magnetometry. And so that's a few topics depending on time we'll look for. So first of all, they are the people who are actually making the lab progress. Dr. Sagar, Anirban, Nilanjan, Sai and Abhishruta, Alan, Pankaj and Bhimit, you all will be familiar with now. They are probably all there, and they are working in the group. Maheshwar, Gaurav and Shayari, they have completed their PhDs. Actually, Anirban and Sagar also have completed PhD from our group, and then they had joined back as a senior scientist now. And Maheshwar is in Israel. Gaurav has shifted to industry, and Shayari has gone to Singapore to become an independent researcher. And I must thank Professor Dibyendu Roy for all these years of collaboration. Professor Supurna Sinha, who had been a mentor and collaborator, and Professor Sanjukta Roy, who will also give a talk, and she is also an organizer, and we do a lot of work in collaboration. Okay, so a snapshot of last few years work, what we have been doing. A few of them I could couple in. So those in the group who do not find their paper here, please don't mind. So these are some pictures which we had given. Now particularly I will try to spend some time on this real-time local probe of atoms using this so-called Raman-driven spin spectroscopy, as well as some magnetometry applications. And then some of the other work what we do, I will also touch upon depending on the time we have. Okay, so we have to also say that India has a very serious national quantum mission with distributed facilities all over the country. I'm very happy to say that quite a few of our collaborators in institutes like IISCR Pune, Professor Umakant Rapol, and in Rajesh Nath, and also IIT Patna. You heard yesterday a talk from Utpal, and you will hear talks from Ajay Vasan and some other members who are close collaborators of ours in this project. They could not come. So we have a nominal leadership role, but we don't work in that mode. We are trying to develop technology in a distributed fashion so that there is a general national facility building. And so it's mostly a technology project. So I will say a little bit about this, and then we will go to the science, what we do. So these are the people. You have already seen Professor Umakant and Professor Rajesh and Utpal. Other members could not come. So we are building, quite a lot of work have progressed with the rubidium atoms in optical tweezer array. The target is to have a 2D array of 400 qubit defect-free system, and also a lot of progress has happened with the calcium ion-based system, which is in the IISR Pune, which is in the western part of the country. And so our platform, we gave a name Anvika, and I just also wanted to highlight that we do indeed have a startup. Anyone wanted to talk about is Anirban and Sagar, so which is a RITComp, which we are planning to have a full stack solution for any quantum computing application. Okay, so the basic idea, since this is a tutorial, is that like in many other groups, like in QERA collaboration and also in Pascal and many other groups where people trap single atoms. So these are single atom fluorescence signal in a defect-free array, and first ascertain that these are single atom by looking at the fluorescence photon coming out of the single atom, shine Rydberg exciting to photon laser. Ours is exactly the same scheme. We do have two schemes. Sanjukta will talk about in her lab how they excite, and here we are planning to make the 420 and 1013 nanometer excitation for the Rydberg excitation. And this atom array is created using a special light modulator and the acousto-optic deflector kind of thing. So just wanted to show that QERA and Pascal are not the only groups. Recently there was very nice demonstration of a very large number of tweezer array of cesium atoms. They have gone up to 6,100 cold atom setup, and people are getting quite excited about this. So some people say that it's how good you do the optics to create the array, because typically even in our lab we shine the optical tweezers from outside the glass cell, and there is a challenge how much scalability is possible. On the other hand, there is also this kind of ideas where people are using photonic integrated circuit, nanophotonic devices to create an array on top of nanophotonic devices. We have also started some work in the lab where we are coupling light, the trapping light, onto the photonic integrated circuit to see that the cold atoms are transferred there. So that's one direction we believe is a possibility for scalability of this thing. So of course, some very nice development along what people call quantum annealing or analog quantum simulation is where you create this defect-free array. I will talk about this, how these things are done, and there is also a poster outside where group members are showing what exciting things we are doing now. And then once we rearrange and try to excite the atoms to the Rydberg state, there had been wonderful talk from Alexei on Rydberg excitation, Rydberg blockade, and because of the blockade physics depending on the geometry, one can see that the readout state will show particular arrangement, and that is kind of a solution of an extremely difficult problem like a checkerboard phase or many other phase with this kind of a long range interaction. There had been a lot of work. I just indicated one, and really fascinating work on the quantum analog simulation and so on. Of course, some people can say this is like an Hamiltonian engineering, and which is also nice. So Rydberg excitation I will just skip through because you have learnt a lot, and also in Sanjukta's group there had been a lot of work recently. So we are using most of the Rydberg entanglement generation, learning from them and just implementing in our system. Okay, so there is a very nice reviews of modern physics by Mark Chapman, and where all these energy scales are given, and also how to do this control phase gate using the Rydberg blockade, and our recipe is exactly following the same. These are typically the hyperfine states. And just continuing on that, since we can move these atoms using the acoustic deflector, just by changing frequency on the acoustic deflector, we can create entangled pair. In our lab, we have not yet done that, but we are working on it. Very soon we are hoping that we will show this, and then we can move them apart, and at least in the optics part, now we have kind of benchmarked our system so that all these things are done in time scales which are agreeable to our experiment, and then this entanglement transport as well as readout. So those things are taken care. Okay, so just going back mostly for the students, since it was a tutorial, I was not sure what to say. So the trapping is typically done by very, very tightly focusing a far off resonant laser light. Typically the trap depth goes as intensity of the laser light divided by the detuning, and we don't want too many scattering so that atoms will be knocked out of the trap. So we keep the detuning very far. In our case, this is rubidium atom with their transition wavelength 780 nanometer. We keep the trapping laser at 850 nanometer. So it's very, very, very far away. So there is practically no scattering per second. It's a negligible number, at the most a few photon scattering. So the lifetime in this kind of traps are very high. But in order to have a significant trap depth of the order of a millikelvin, which I think I have written here, so we need a reasonably high power laser focused as a shorter distance. So of course this is an example. So this is what we do for the crossed dipole trap in our kind experiment, but for the quantum computation we actually focus down to 1 micrometer using a microscope objective. So at that 1 micrometer, so the trap depth can be very high. And so here an example. Typically, since this trap depth are millikelvin, we cannot hope to capture an atom from the background. We need some pre-cooling. So this is why we do laser cooling and trapping, subdoppler cooling, and all sorts of things. And then we transferred these atoms. For example, here you can see that once we focus in a laser light onto a bunch of atoms after doing some subdoppler cooling, etc., we have a lot of atoms. I'm sure Sanjukta will show a nice picture of few atoms, and we are also going to show some pictures at some time soon. And then, we do a lot of things. Then the idea is to actually have many such traps. How do we create that? So we create using devices called special light modulators. We create a hologram, and then we shine Gaussian light onto the hologram, and that light is focused through the microscope objective. Yeah.
Very naive question. So these atoms in different traps,
Hmm.
do they talk to each other?
We can make them talk to each other. Yeah, sure. That's actually one of the thing when we say that we create an entangled pair and then transport. So what typically you do, so there is something called a Rydberg blockade radius. If you excite these atoms, for example, to 2 photon excited state, and they come close to this blockade radius, then one atom can be in the Rydberg state, the other one cannot be, or vice versa. You don't know which one, so it's like a which path information. So that is how you can say that how you create the and then you can take them apart, and you can actually show, people have shown that even when you take them apart, so the Bell state fidelity remains intact. And these are like, when I read these papers, it's like science fiction, but indeed, so now we create this using 2 types of devices. One is called a MEMS device. It's a digital micromirror. So we have worked with it for some time, and then create all sorts of potentials. We can even impart some angular momentum to this atom. So those are the things I am not talking about in this particular talk. But here we can create this light pattern, and then this light pattern are shining onto the trapped atoms, and then we typically create. So these are some things we pay a lot of attention, how to make sure that the intensity is uniform of the order of 1% across the tweezers, and then so even then something what we have to pay attention is that the loading in the single atom traps, they are stochastic, so not that all atoms get trapped in each point. In some of the places there can be one atom. In some places, if there are more than one atom, they collide with each other. This is called collisional blockade, and then both of them goes out. So there will be some empty spaces also. And in order to do a meaningful quantum computation, we first have to make a defect-free array. So you have to take an atom from somewhere to bring it to a region where you first create that defect-free array. So that is something has to be done reasonably fast. Right.
What is this in the top left image? What
This-
is this? Top.
Oh, so these are just the light pattern spacing. So we make sure that the spacing between the two trap is 4 micrometer. That is to make sure, sorry, 5. Yeah, 5. So of that order. And and then this algorithm, typically these algorithms are executed using FPGA based control system. There are nowadays expensive solution to that. There are companies who can sell you the entire box who can do it, but we are going the traditional way with our own FPGA programming and controlling the acoustic deflectors. And then detection is, so far we have been doing most of the detection with EMCCD, but recently we have started using something called a QCMOS camera. So that is the general direction. And of course, these are something which we have not done yet. For us, the keyboard is to make a 2-photon Raman transition from one of the hyperfine state to another. So we designate one as state 0 and state 1, and depending on the pulse time, pi by 2, pi pulses, we can actually make sure the transfer from one state to another and execution of quite a few gate operations and so on. I hope that sometime soon we should be able to do that. Okay, so I change gear to the other experiment what we do. We have simultaneously laser cooling and trapping of sodium and potassium atom. Potassium we trap a large number of them.
something of the order of 10 to the power 10 routinely. And sodium, so far we were a little bit limited because of our laser power to something like 500 million. Recently we have upgraded the system with a very, very powerful laser. So we are hoping that we will have a large number of sodium as well, so that we can increase this number also to 10 to the power 10 and simultaneously do that. We do have 2D plus magneto-optical trap, which works very well to give a very fast loading rate. So we typically can trap within a second this 10 raised to 10 atoms. And since the two clouds are trapped inside this central vacuum chamber where the 2D plus modes are loading from two sides, this is this two-dimensional transverse cooling. So we have a geometry where simultaneously both atom clouds can be trapped. After trapping, we transfer them to a pure magnetic trap, switching off all the cooling light and so on, and transport them to the science chamber, I think, yeah. So, so then, and before that, we do take different stages at the magneto-optical trap after compressed mode phase, and then transport the cloud. We are optimizing the transport efficiencies and so on. Transport efficiency is quite good, but pushing for the evaporative cooling in the cross dipole trap. So this is one direction what we are taking. Okay, so let's talk about some science experiment we were able to do before the many body BC and Bose Fermi, because we do also have the facility of changing the isotope of potassium to a fermionic isotope, which is potassium 40. So physics. So one thing we can do, we can tune interaction between the atoms, not yet with the fetchback, but with what is called the photo association with cold molecule formation. For a short time, we can create a large number of molecules, and then once these molecules are formed at ultra cold temperature, they have two options: either they leave the trap or they gain interaction energy to boil out of the trap. And then we were asking the question starting that even when this kind of short range and short term interaction is tuned, what happens to the motion of the atoms in the trap. So we, sorry, okay. So we had looked into a few of these effects. So we tried to see what is the effect of this light assisted tunable interaction to this position respect. So we take an atom, we move it a bit from the trap center and we leave it. So this atom is supposed to do some damped harmonic oscillator motion. Now if you tune this interaction between atoms or between two separate species, whether this damped oscillation becomes even more damped or something else happen. So this is what we do. We give a kick and we try to see what is happening. And then to our surprise, so this is the cartoon what happened. We create this molecular state, and then what happens is that usually one would expect that whenever you introduce any new interaction, these atoms are supposed to become even more damped, but it actually became accelerated. So we asked the question why this is happening, and then our theorist friends, they also calculated using a Langevin equation prescription, and they found that what is happening, there is a collective motion. So once an atom goes to a particular dipolar state, so it kind of drags all of them nearby, and then they are making a collective motion, and that collective motion is very nicely captured using the experiment and the theory. And we could even make out that if we tune the interaction exactly on a molecular resonance or outside, then we can see whether there is a overdamped motion or an oscillatory motion. And it was something which can be also highlighted, that by just tuning interaction, we can try to make the charge motion in some semiconductor system accelerated, so it can be some kind of a charge transfer. And this is more like a single particle physics, not yet many body effects coming in, because this is far above the quantum phase transition. So this is like a few microkelvin temperature where we did this experiment, but we are also trying to see what happens if we do the same experiment in a case of a BEC-BEC mixture. So we yeah.
How are you moving? It's not working, but it's okay.
Yeah.
How are you moving your atom?
Yeah, so we do two things. In first case, we give a magnetic kick to the atom cloud. In another case, where we wanted to make a very specific region, not one atom, but a few of them. So we focused a laser light, very weak laser light, so that not to knock them out of the trap, and gave a short pulse, and then they moved to the trap. Short time pulse, and also very weak pulse. So there are two ways. One, we give a optical pulse. The magnetic pulse kind of moves everyone. Optical pulse, we can choose which one to do. So since we have two types of experiment, this was done in potassium while tuning the potassium-potassium interaction. So there we did not care much whether we are moving all of them or one or two of them, because finally it's like a single particle physics, all of them should mimic the same physics. Whereas when we do the sodium-potassium, sorry, these measurements are not there. They would be there in another paper. So so I can show you later. So there we could actually maybe at the very beginning I had this. So we could create a cloud of sodium as a bath and make a few potassium atoms moving in the bath. In presence and absence of them, we did indeed see that there is a change in the motional frequency. And this can be nicely captured using the Langevin picture. So that's
What's the typical
time scale.
displacement? Yes.
So we do displace of the order of millimeter. Yeah, it's quite a lot, because finally, we allow them to move in the trap. It's a big cloud. This is not BEC. This is above the BEC, and we just try to see what is happening of the cloud. So yeah, here I think.
What's your initial temperature?
So initial temperature is, I think, 50 microkelvin. Yeah. So it's very hot. Means it's not. It's not like 50 nanokelvin. Yeah. So it's cold compared to here, but so. Okay. So so of course these are nice, of interest, but these systems have serious limitation detection. And typically, every one of us getting very excited doing nothing. We do fluorescence or absorption detection, and these are all destructive detection. So whatever, there is nothing quantum after one detection is done. So then we thought that why not we use something we learned from Dibyendu, use our spin noise as a detection technique. So that's what we did now. Recently, how much time do I have? So.
You have 50.
Oh, a lot. My God. Okay. So now we have now applied this so-called. We don't want to call it quantum non-demolition. It's more of a non-perturbative detection. But since it's kind of a projective measurement and so on, sometimes it goes okay. Means compared to other people, I'm not making many high claims. So now, so we look into this spin in the atom. So we are always talking about the hyperfine spin, F number, and then you had also seen the spin states in Dibyendu's talk, and we are looking at how the atoms are fluctuating between this state. I will very quickly go through this part so that but give another aspect of this. So these are tiny magnets, the atoms. So when they are in one of the state, they will be precessing, and then when they go from one spin state to another spin state, they are suddenly changing their precession direction, and that's what we detect using this kind of a Faraday rotation detection. So we do detect Faraday rotation from cold atom also. There had been a lot of work in this non-destructive detection of atoms using Faraday imaging, using phase contrast imaging. So you might find a lot of these papers from other groups. So we look into this so-called this Faraday fluctuation, and this Faraday fluctuation detection is done exactly the way Dibyendu say. We have this bunch of atoms, and then this is like making a Johnson-Nyquist noise detection. So instead of measuring the resistance by looking at the Ohm's law, we are measuring the fluctuation of the voltage, and then also we measure. It's like, you know, holding your nose by rotating your hand, but still it works. So then we are actually making this detection magnetization in time, and its Fourier transform is actually the frequency space. So we had done some work previously also. I will not get into that. But then we had also started driving this bunch of atoms using another pair of laser light, using this so-called 3-level system. And since these two light looks like this addressing Stokes and anti-Stokes drag, and we are in Raman Research Institute, we decided to call it Raman drive. So if you like or not, then we do this kind of a Raman drive, and then we can actually drive, and then depending on how good we are in phase stabilizing these two laser light, we get an extremely narrow, and it's supposed to be a delta function, but still there is some small width is because of the small frequency jitter we have in the two acoustic modulators, and that is something what we are trying to reduce by phase locking using the phase lock loops, and now we can do extremely narrow Hertz level stabilization. These measurements are taken with some kilohertz line width. So once this is done, we had also used it to see, for example, time varying magnetic field. We continuously monitor by exactly applying an external magnetic field which is varying over a time scale of heartbeat, just to see, and also the magnitude is given what is the amount of magnetic field produced outside your body, and we can actually see that the signal follows, this is like a non-invasive detection of biological functions or something like that. And also we can use it with a nice model that the direction of the magnetic field. So this is both vector and time result magnetometry. Just wanted to, since I have few minutes, magnetometry has a lot of application, so it can be used for navigation, exploration, and so these are like digital compass, and can also be used nowadays, you know, brain waves and so on. I hope that our detection can be made small to wear on a headband, and then of course there is a lot of science and technology which can be developed using that. Of late what we have done, that is really thanks to Shayori, so that we have recently done this work, so where we can actually change the external magnetic field with this driven system, and even in real time we could see that how the spin resonance can be used for detecting a magnetometry. So for example, here we can just have a small external magnetic field of the order of a few tens of picotesla. We are trying to make it to the femtotesla, but one good thing is that we can do this measurement in presence of external magnetic noise. We don't have to really shield like all other magnetometer, because this is like a self heterodyne detection, so there is no need for external shielding. And this is one high point we wanted to share. For example, here we actually made an external magnetic field come onto resonance, and then on a oscilloscope we could see that spin resonance can be seen, and we can detect very, very precisely of the order of I think to 30 picotesla per square root of hertz, looking at the spin noise signal amplitude above the background. So this needs to be compared with present day state of the art magnetometers, atomic magnetometers, which typically work in femtotesla per square root of hertz, but they saturate at a very, very small magnetic field because they are always looking at rotation itself. So here we can deploy this magnetometer here in this room. So all these measurements are taken with or without shielding, so and we see no difference at all. So that's one point what we try to see. So just the last point, so we can actually now shine this spin noise signal through this bunch of atoms, and we can actually see again the time dependent signal, And now see, since we can set our external magnetic field of the order of a Gauss, which makes the resonance of the order of a megahertz, so this detection is a microsecond detection scale. So in a microsecond, and we are actually detecting, for example, this is femtoliter. So that is the kind of volume one tweezer trap has. So it's 1 micrometer. Of course, these measurements we had taken with probe light focus to 35 micron, but that's for benchmark. But one thing what we want to do, suppose we put the probe light to the same micrometer where the atom is supposed to be there, so we can actually clearly distinguish if there is 1 atom or 0 atom in that femtoliter, that is 1 micron by 1 micron by 1 micron. This is something, and without knocking that atom, without making sure that the atom goes from one state to another, because this is actually a non-invasive detection. We can do that. Don't worry about the fractional atom number. This is just because of the normalization. So, so the idea is the following: when you do quantum computation, typically the detection of the fluorescence people capture of the order of 1 to 10 or 20 millisecond. But we are actually detecting, look at this, this is of the order of 1 or 2 microsecond, and we do see a lot of oscillation, and that way we can actually make sure that the detection can distinguish, and also the frequency of this is different for f equal to 1 or f equal to 2. So that means if I call it, because the g factors are different, if I call it this state 0 or state 1, we don't have to really rely on the fluorescence. Okay, okay, but questions can be there. I don't think, okay. So just to show that we can actually see a time series where we were adding more atom to our trap, and kind of like grew. For example, typically people do a fluorescence detection of these atoms coming from there, and when we do, for example, this Raman driven spin noise signal, that actually grows exactly the same way the fluorescence grows. And even better, since we are looking at a local density, so it shows a nice feature which is actually making the local measurement. We also did some moved around the probe position. Okay, this is very hard for us to do. We kept the probe position somewhere, we moved the cloud around, and we actually saw a very nice kind of spin noise signal which is probing the local density, and we moved the cloud the same way using an external bias magnetic field and so on. And then I think referees asked or someone that how do you know that what you are measuring is right or something. So we said, okay, we assume some asymmetry, and then from the fluorescence we can detect the local density, and then that matched using an inverse Abel transform, and so there we can prove that what we are measuring is what we are actually saying. Okay, so I already come to the conclusion that these are nice test bed for exploring fundamental physics as well as quantum technology, funding agencies like this word, quantum technology development. So many complex things happen, and I'm very happy that there are at least 4 or 5 labs in India now who are working with serious cold atom kind of measurements, and then atoms are suitable for quantum computing and sensing, and they are like natural standard. So this is like if you have a superconducting qubit, then who made that this transpond circuit is the hero. But here the atom what you have, I have is the same, so it's not very different. So this is also relatively easy to control atom-atom interaction and impurities in traps. And then atoms' response to external electric magnetic fields are easy to model, and they can be also suitably used for sensors. These are big sensors. These cold atoms are on 2 optical tables usually, difficult to carry, but some of the vapor cell versions are relatively simpler. And so these are a few things I wanted to say. There are some.
So we have 7 minutes for questions.
Thanks for the overview. So if we go back to the last part, the point is to measure the density of an atomic cloud, right?
If you want to measure the density, yes.
But not all the way down to single atoms.
Sorry?
Not all the way down to single atoms.
So these measurements, what we have done is, so for example, okay, I'll show you. This signal, this particular signal, which is one of the faintest what we measured. So we had a spot size of 35 micrometer. So typically in that spot size we have a few hundred atom. But on the other hand, these measurements were not done using a microscope objective to actually focus down the probe. So if we do that, then the signal amplitude for one atom is also supposed to be, because there are people who have
do you think you can get all the way down to a single atom?
Yeah, no problem.
Sensitivity?
Because people have done measurement of Faraday rotation of single atom. They have seen like 3-degree Faraday rotation from one single atom, and we are talking about Faraday rotation fluctuation. So I am not very doubtful why it can't be measured.
I would have another one, but I can come back.
Yeah, thank you. Can you explain again how do you, from the DC measurement, get to the vector?
Okay. This I had not touched at all. See, okay, I have this one. So this is one full paper. So what we had done, we actually had applied the orientation of the external magnetic field. If you followed the Bindu's talk, you will remember that the magnetic field which you apply perpendicular to the direction of the propagation of the probe light. So that is a true measurement of the spin noise. On the other hand, if you make a measurement applying magnetic field along the direction of the probe light, so that is a Faraday measurement. So that is like traditional Faraday measurement. So now you can actually have a spin noise signal in presence of Faraday configuration. So we actually calibrated using actually applying the magnetic field direction, and then we have knowledge of what is the signal strength, normalized signal strength expected, and so that can be used as a vector magnetometry. So it's like a combination of a Faraday measurement and transverse spin noise. Spin noise is a little bit unconventional measurement. It's not really a Faraday measurement. It's a Faraday fluctuation measurement. So it's a 2-time correlation function, but you can do that 2-time correlation function even in a Faraday geometry. So that's what we had done.
Okay, thank you.
Okay,
You can ask after him. Please ask.
Okay, thank you. Okay, so I want to come back to the question that he asked. And I was wondering, so you mentioned the fact that this type of measurement can be very fast compared to fluorescence. As we can see the microsecond scale, but what about the fidelity of your measurement?
Yeah. So this kind of boils down to how well we couple the magnetic states. So you are right. So we really have to pay attention to the Raman beam polarization purity. So we, for nearly 1 year, we didn't see anything. And even today, if somebody makes some mess in the lab, we don't see anything. Because we really have to put everything right. Typically, the polarization purity of the Raman drive has to be very good. So then this kind of, but to answer your question, that suppose there is an atom which is in, let's say, one of the state. You prepare the state where, you know, people say that we have a 99.98% fidelity of my single qubit operation, right? Using a fluorescence measurement. and now I do this measurement and show that, okay, so this is also 99.98%. So this we have not done yet, but this is something what we have to do. See, if I have to prove it that this is the technique, coming back to his question, that it works for single atom, really single atom, then the second thing we have to do that, show that this is really not making the measurement. So there is a lot to do in this direction. But it's just an alternative technique.
So the line width of this spin noise spectrum, is it same in cold atoms and?
No. So
no, why I'm asking is, you said you suspect the phase noise of the two Raman lasers.
So we are limited by that only.
No. Yeah. So is it that, or is it transit time broadening that is coming?
So the transit time broadening in the vapor.
Not broadening. Yeah. Whatever. Yeah.
So Dibyendu can answer that question well, because we.
In vapor we surely have 200 kilohertz. That,
No, is that because you have finite time the atoms are spending?
Light, within the light spot, atoms even moving across and all these things are happening.
So what is the limit?
In cold atom.
No. What is the limit put by that on the line width?
So that's actually of the order of 150 kilo. There are many things. See, we have done this experiment in vapor also with the paraffin coated cell, with the neon filled cell, to make sure that this is. So we have actually made, there was one paper we wrote long about all this broadening effect we investigated. But the cold atom, there is almost no such broadening. So we are limited by only the phase noise of this
in cold atoms
so far. But I'm sure that there will be some effect eventually. So.
Yeah, thanks for the talk. I have one question. Faraday rotation and quantum non-demolition measurement, they have been used to produce a spin squeeze state. Is it something that you could explore in your experiments? For
Very
example,
nice.
for magnetometry?
Yeah, very good question. So we are exploring two things. One is that we are planning to use squeezed light as a probe. So this is one. And then what you are saying is that even spin squeezing the state of the atom itself, when we trap one atom in the tweezer, so that's actually on the cards. Thanks for this question. We want to do that. Yes.
Yes, thank you for the nice talk. Just wanted to ask about this, your density measurement. Do you need to calibrate your measurement here, or is it an absolute value that you get from your experiment?
Yes, for this, referees asked us to calibrate. So we did the calibration using the fluorescence and absorption measurement. But now that we know that it's kind of, means if you are asking this, so this was like a calibration. So we know that what we are measuring is, because typically for fluorescence and absorption measurement, you don't directly measure a density. You measure some kind of overall signal, and then you assume what is the density, which is the wrong thing to do. But there are prescriptions to do it by assuming some symmetry and then applying Abel transform to say that what is the density. But since we are focusing to a very small area, we don't have any signal from outside. Because even this, I didn't talk about this spin noise has some very nice property. The signal actually comes from the focal plane, slightly away from the focal plane. The signal strength, spin noise signal strength is very small, because it goes as inverse to the area of the probe light. So when you are focusing tightly, so we are almost safe in saying that we are seeing exactly from where we focus in that mode field diameter. So it's actually a density detection, and moreover it's that particular state detection, because there's noise between the adjacent magnetic state. The other noise from one F state to another F state, so that is typically in gigahertz away. So we can detect that, but we have not detected. So.
Can I ask one more?
Sir, I have a basic question. In your implementation, you have shown that you are using 2 pulse protocols.
Yeah.
It would be pi or 2 pi
Mm-hmm.
pulse, instead of using single pulse protocol, which is sometimes I feel better to use single pulse, because when we switching 2 pulse, among two pulse, then there would be some error may create, or sometimes shaping the single pulse time dependent
okay,
pulse,
okay.
it would be better to like
I
reducing
know,
the
yes,
population
yes.
leakage and all. So
No, I know what you are asking for.
Yeah.
We have not gone to that level of pulse shaping and so on, but we will look into that clearly. Means we are discussing with Ajay ji, and so I know so where the question is coming from.
I just have a related question regarding this measurement with the atom density probe. So this measurement has been done only with the one species, right? But you have a system of two different species, sodium and potassium.
If you allow me, I think just 1 second. Sorry. Okay, so I omitted all that. Yeah. So we had some preliminary measurement. So what we have is that suppose I have a potassium measurement. This is some preliminary, and then we do see. Now, if we have another species, so these are what? You have some magnets which are around. So this is changing the local field, and this change of local field we seem to also capture. This is, Shairi is also too busy. So we are, but this is a good direction. So we wanted to use this as a probe for the spin exchange. So you can actually make spin state of one species, and while on live you can introduce some spin polarization of another species, and we do indeed see that live the spin measurements shift from one. Thanks for this.
So the interspecies interaction is through the magnetic field.
Yeah. So you have to do some work on that.
In general, these atoms have like an exchange interaction, right?
Yeah.
Like one like rubidium, it goes from one unit level to another, and similarly potassium can go from down to up. So that's like spin exchange interaction.
Yeah, so this is quite preliminary. I don't even know that whether they should go in this direction or that direction, but that's what. So that's kind of a little bit of a style in our lab, that we see what we can see first, and then we try to see that whether, but other way is dangerous, no? So if someone says that, look there. So
Okay, thanks.
Okay, so I guess you have a lot of questions. So we finish. You guys have some questions?
So we have a 15 minutes tea break now outside, but we have to be on time. Please have your tea and quickly be back in 15 minutes. happy Bastille Day to all the French participants. So today I'll be talking about quantum science and technology with ultra-cold Rydberg atoms, and I'm happy that I'm giving this talk just after Fabien because it made my life much easier. I can skip through the basics. So the outline of my talk is I'll give a brief introduction to quantum technologies with Rydberg atoms. I'll briefly tell about our measurements of transition frequency of very highly excited Rydberg atoms. And then I'll talk about some interesting results we had got in our lab in the past few years. One is Doppler enhanced quantum magnetometry with Rydberg atoms and quantum sensing of microwave fields with Rydberg atoms. And also I'll describe the effect of interaction on Ortler-Town splitting in ultra-cold Rydberg atoms. And finally, I'll give a future perspective on scalable quantum network and quantum sensing with optical tweezer arrays with individual Rydberg atoms. Talking about quantum technology with Rydberg atoms, quantum technology has 4 broad regimes: quantum computing, quantum sensing and metrology, quantum simulation, and quantum communication. And I'll show that Rydberg atoms are such a versatile platform that you can explore all these regimes of quantum technology with Rydberg atoms. So Rydberg atoms, because of its very giant size, because the electron is very, very high up in a very highly excited orbital, so it gives Rydberg atoms a giant size. So these are the giants of the atomic world. So Rydberg atoms were discovered way back in 1888 by Johannes Rydberg, and this played an important role in the birth of quantum mechanics. So why Rydberg atoms are so interesting for quantum technology? Because of its very highly excited electron, Rydberg atoms have very high dipole moment, and this gives Rydberg atoms several exaggerated properties. For example, they have very large lifetimes, which goes as n cube, which gives long coherence time to these atoms, and it's very important for applications in quantum technology. Another very important property of Rydberg atom is that it has very large polarizability, which goes as high as n to the power 7. So it makes Rydberg atoms extremely sensitive to small DC or AC electric fields, and hence they are very, very useful for quantum sensing and metrology. Another very important property of Rydberg atoms is that they have very strong interatomic interaction. The dipole-dipole interaction goes as n to the power 4, and van der Waals interaction goes as n to the power 11. So you hardly see any physical parameters so strongly dependent on the principal quantum number, and this has very important applications. We can create quantum entanglement using a Rydberg blockade effect, which enables the creation of fast quantum gates for quantum computation. We can do quantum simulation of many-body physics in condensed matter systems, and also they are very useful for quantum communications using strongly interacting Rydberg atoms as a single photon source. So let's make a quick comparison of the Rydberg atoms with atoms which are excited to low excited state. For example, you can see the sizes vary are differed by 4 orders of magnitude. The lifetimes of the first excited states are like in nanoseconds, but it can be like 10 milliseconds for Rydberg atoms, and for circular Rydberg state it can be as high as 1 second. So you can see the range of interaction for Rydberg atoms is much larger as compared to first excited state, and also the level spacing is in microwave frequency, so they're excellent quantum sensor for microwave fields. So actually the Rydberg blockade effect was described very well today in earlier talks by Alexei But for completion, I'll just very quickly go through it. So if you have one atom in the Rydberg state, and if you bring another atom close by, because of the strong interaction, there's energy level shift. If you excite one atom to the Rydberg state, because of the energy level shift, you cannot use the same laser to excite the other atom to the Rydberg state, and vice versa. So you create a correlation between these two atoms, which leads to quantum entanglement between the two atoms, and eventually fast quantum gates. How do we detect the atoms in the Rydberg state? Using Rydberg electromagnetically induced transparency. So I will not explain it because it was very nicely explained just in the talk before. So we have a ladder type of system. We have a probe laser at 780 nanometer exciting the atom from the ground state to the intermediate state, and from the intermediate state to the very highly excited Rydberg state, we use a 480 nanometer coupling laser in the blue regime, where we get a Rydberg electromagnetically induced transparency signal, which basically is because of the destructive quantum interference between the transition probability of this two transition. So these are the Rydberg EIT signal we get, and here is the picture of our lab, and you will see this when you visit our lab on Thursday. When we had started the experiment on Rydberg atoms, we wanted to go to as high Rydberg state as possible, because higher we go in principal quantum number, the more interesting are the properties. But at the time, the measurements for these frequencies were available only till n equal to 55. So we made an accurate, comprehensive, accurate measurements of these transition frequencies all the way to 125. So here you can see the measurements for transition frequency. We had like a measurement conservatively like around 2 megahertz, but most of them were as accurate as less than 1 megahertz. So we could also get very accurate measurement of the quantum defects from these measurements. You could see here, these are the data points, and as you go higher and higher in Rydberg states, because the level spacing are become smaller and smaller, it's like almost continuous. So these were our measurements a few years back. I come to the next result which we got in this setup, which is Doppler enhanced quantum magnetometry with Rydberg atoms. Here I would like to mention that this probe and the coupling laser were counter propagating in that cell, and so as to compensate for the Doppler effect, but we cannot compensate completely because the wavelengths are different, and this leads to what is called a Doppler mismatch. What we found that apart from the Rydberg EIT signal, we got another broader signal. We had this extra signal. We were very surprised, and to understand it better, we put a magnetic field in the setup, and to our surprise, the Zeeman shifts, or the response to magnetic field of this another signal, was an order of magnitude higher than the Rydberg EIT signal which we got from the counter-propagating beams. So this was from the co-propagating beams. So actually it turned out that we had, the other signal was coming because of the back reflection from the cell which was making the beams also co-propagating. And so we had this very surprising result, and we wanted to understand it better. So we collaborated with Shobhan Datta, who is an in-house theorist in RRI, who is also here in the workshop. And we worked out the theoretical modeling in collaboration. And here you could see the theoretical result, which matches very well with the experiments. This was published 2 years back, and also was highlighted by DST and the media. We also got the similar results for both the linear and the circular polarized light. So why it's so important? Because high sensitivity magnetometry has a lot of important applications like navigation, geophysical and mineral exploration, archaeology, security, and space exploration, of course, military and medical research. So now I come to the next part of my talk, where I describe our project on.
There is a question.
Yes.
Maybe I missed it. So why is it so much more sensitive to magnetic field?
So actually, because of the Doppler shifts are not compensated, Doppler effect is not compensated like in the counter propagating. So they are accessing more and more energy levels, and the Doppler shifts of those energy levels are also contributing. So if you see in the theoretical modeling, the condition which we found for having this the higher sensitivity is that the intermediate, the Zeeman shift at the intermediate level should be either larger or smaller than the Zeeman shift of the ground state and the Rydberg state. So this is the condition which we found from the theoretical modeling. And here you could see this is the relation which we found between the sensitivity of the counter propagating and the co-propagating fields. Okay. So I come to the next part of my talk where I talk about quantum sensing with Rydberg atoms. So this the basics of this was already described by Fabien. We had seen a 3-level system where we get the Rydberg EIT, and when we put a microwave or a radio frequency field, then we get a 4-level system where the successive Rydberg states are coupled through microwave, radio frequency or terahertz field. And so the Rydberg EIT is then split because of the Ortler-Town splitting, depending on the power of the microwave field we are putting. And here you could see the Ortler-Town splitting because of the microwave field. This was described very well, the basics of it in Fabien's talk just a while ago. And so for smaller microwave power, we just see a broadening, and then as we increase the power, we see a bigger Ortler-Town splitting. And I would like to mention here that Rydberg atoms are versatile in the sense that depending on which Rydberg states we are choosing, the difference between successive Rydberg states can be in terahertz for lower Rydberg states. In the intermediate Rydberg state, it can be in the microwave regime, and in very higher Rydberg states, it's in radio frequency regime. So we, as compared to classical sensors, we don't have to design different classical sensors for different range of frequency sensing. But it's the same Rydberg atoms which are a versatile quantum sensor for a wide range of electromagnetic radiations. So I give a quick comparison between the classical antennas and Rydberg atom sensor. Another very important advantage Rydberg atoms have got is that they are calibration free. So the accuracy of classical sensors lies in how accurately we calibrate. But Rydberg atoms are self-calibrating, so they are the same everywhere in the universe. They are free from man-made defects. So that makes Rydberg atoms a very versatile quantum sensor for a wide-band quantum sensing of electromagnetic radiations. And there are, of course, many problems like mutual coupling of antenna arrays and design complexity, degrading performance over time, like any man-made fabricated system, and these are not there in Rydberg atoms. So these are the future quantum sensor we are going to use. So this is our setup in our lab for microwave quantum sensing with Rydberg atoms. So you can see it when you visit our lab on Thursday. So here you could see this chamber for microwave sensing, and these are microwave absorbers to prevent standing wave for accurate detection of the microwave fields. So here we could do a very high sensitivity quantum sensing of the microwave fields, and we could detect as low as -60 dBm, and we hope to go to target power detection of -150 dBm, and we are also planning, instead of a single vapor cell, we are planning an array of micron size or millimeter size cell so that we can have improved quantum sensing of this microwave fields. And I'm happy to inform you that recently I've got a grant of 1 million euros for this project to make a prototype for this microwave quantum sensor. So these are different results for frequency and amplitude modulation, which we got in our lab. And here is some results for amplitude modulation with of the microwave fields. So this we are characterizing to understand our quantum sensor better and characterize it better. So of course, there are very important applications of Rydberg quantum sensor like wireless and satellite communications, radar sensing, remote sensing, navigation without GPS, atomic clocks, gravity detection, and of course, radio astronomy. So this was our, these were our experiments on room temperature atoms, and now I go to Rydberg excitation in ultra cold atoms, which is my area of expertise. So this is our setup for cold atoms in our lab here in RRI. This is the picture of the cold atomic cloud. And we have two detection systems which helps us have very accurate and very high sensitivity detection of atoms in the Rydberg state. One is of course the EMC-CT camera, and we have a single photon counting module. And we all have two of them, and we also do second order correlation function measurement with this setup. So this is our schematic of our Rydberg atom experiment. So we use our cooling laser beams to excite from the ground state to the intermediate state, and from the intermediate state to the Rydberg state using the coupling laser. And what we get as the signal from the cold Rydberg atoms is this Ortler-Town splitting signal. The high intensity, the cooling beams, they create a AC Stark shift, and the coupling and the Rydberg laser at 480 nanometer is probing this transition, and we see this Ortler-Town splitting. So here is the signal from the Ortler-Town splitting, and we had several publications on this. So one very interesting thing we saw in this signal is that as we go to higher principal quantum number, this Ortler-Town splitting signal is broadening because of the dephasing effect of the Rydberg, strong interaction between the Rydberg atoms. And we found something very surprising, that as we go beyond n equal to 100, the signal is completely distorting here. And this was because of the very strong interatomic interaction between the Rydberg atoms, which eventually gives rise to a Rydberg blockade effect, which is the basis for quantum entanglement between Rydberg atoms. This was published in New Journal of Physics. We did a theoretical modeling with, in collaboration with Rajesh Nath, who gave a talk this morning, and you see there's an excellent agreement of our experimental results with the theoretical modeling. So this was published last year and also highlighted by DS Department of Science and Technology and Media. Here are different publications we have from our Rydberg atom experiment. Of course, as we want to do quantum technology with Rydberg atoms, we want this Rydberg atoms to be ultra stable for a long, long time, to have larger coherence time, longer coherence time in the system. So we are locking these two lasers to a reference cavity, which we got from stable laser systems. So here you see that we have measured the finesse of this cavity using the ring down method. So we could reduce the line width of the lasers from 500 kilohertz to a few like 20 to 30 kilohertz, and we hope to go to even smaller line width like 1 kilohertz soon, so that we have longer coherence time in our cold Rydberg atoms. We got the evidence of this long coherence time due to the locking to the cavity of these two exciting lasers. Is that you see here, without the locking, you see a very noisy signal, and here it could stay stable for a very long time, and with very clean signal with the locking to the cavity. So here you can see the signal. We have submitted this results in a journal recently. The next step in our experiment, which we have advanced quite a lot, is to have individual atoms in optical tweezer. For that, we have two high numerical aperture lens inside the vacuum chamber, which creates an optical tweezer of a focal spot of 1 micron. This is important because if you have 1 micron focal spot, if you have more than one atom in the trap, there will be light-assisted collisions, and if there are more than one atom, both of them will go out of the trap. So either you can have 0 or 1 atom in the optical tweezer. So we already have some micron focal spot in our optical tweezer, which enables single atom trapping. So here we have an array of optical tweezer showing here. And we have made quite a lot of arrays of optical tweezer in our experiment using spatial light modulator. So we have also written the name of our lab with the array of optical tweezers. Our name of our lab is Quantum Optics, Optics with Rydberg Atom Lab, Coral. So we have written it using array of optical tweezers. So we already have atoms in our optical tweezers. So we started with a larger tweezer, but we had a lot of atoms in the trap, so we reduced the trap size further, and now we are optimizing our detection system, and we could detect as low as 9 atoms, and soon we hope we can detect single atoms. We just have to optimize our detection system. So we have also used acousto-optic deflector to make different kinds of optical tweezer array, and we have complete control over them to move move the distance between them. So we have, it's a completely controllable system. So with this very controllable system, we have a few future directions once it's up and running. The idea is to have individual atoms trapped in an array of optical tweezer, and then create Rydberg excitation and create quantum entanglement between them using Rydberg blockade, and create a large scalable quantum network of this Rydberg atomic qubits. We are also, instead of a vacuum chamber, we are building up a new generation of experiment with glass cell and a microscopic objective, so that we can have a high resolution detection of this optical tweezer array. What are the physics we want to do with this? So we know that in microscopic systems and non-interacting system, it follows single particle physics. And in macroscopic system, in a strongly interacting system, it follows many body physics. But the regime in between, the mesoscopic regime, is very interesting. What happens between the microscopic and the macroscopic regime? And Rydberg atoms, because of its giant size, is just perfect to explore this very interesting mesoscopic regime. The idea is to have atom by atom assembly to go from this microscopic regime to explore this mesoscopic regime and create a large scalable array of this 1D or 2D array of Rydberg atoms. And there are many body physics we can do with it. There was some demonstrated in the group of Antoine Brouwer's. We can have them in triangular or square arrays and look at antiferromagnetic ordering in such a system. We can have, combine this long-range interaction in Rydberg atoms with disordered potentials. I have experience in working with Anderson localization of BC in a group of Massimo Inguscio, where I did my postdoc. And we can look for new quantum phases in such a system. There's another very interesting regime we could explore is like spin glasses. So spin glasses are a very interesting system. So suppose you have in a triangular lattice, you have two spins pointing in opposite directions. So you have two spins in opposite direction, and the third one is confused which direction to point, so it's frustrated. So this makes a frustrated system. And so if you have random coupling or disorder plus and frustration, you make what is called the spin glasses. And there are several models which can explain spin glasses, like Edwards-Anderson model or Sherrington-Kirkpatrick model. So, but there's many open questions which is the correct explanation for such interesting system. And so Rydberg atoms in such triangular lattice, they provide promising pathway for experimental realization of quantum spin glasses using programmable amorphous Rydberg atom arrays. And there recently has been a theoretical paper on quantum phase transition from a paramagnetic to a spin glass phase. So there are a lot of possibilities in such a system. Also with ultra cold atoms, we would like to do quantum sensing with individual Rydberg atoms. And we hope if we can beat the standard quantum limit using quantum tricks such as squeeze states and reach the Heisenberg limit, which is the holy grail of quantum measurement. So I have shown that Rydberg atoms are a very versatile platform for exploring the various regimes of quantum technology like quantum computation, quantum simulation, quantum sensing and metrology, emulation of complex solid state system, many body physics, ultra fast quantum dynamics we can also do, and also we can use it as a futuristic dipole antenna for observational astronomy. So it's a versatile quantum system. So it's one of the most important slides where I show the people who have done this work, which I've shown in my talk. Yashika and Ashwara, you see them around. They're PhD students working on quantum computing and quantum sensing experiment. Shilpa has completed her PhD and doing postdoc with Christian Gross in Tübingen. Shobhan has just completed his thesis. And Abhinash and Briganka, Abhinash is a PhD student, and Briganka is RA who is also going to start his PhD in France. And they're also, they not only excite atom to the Rydberg state, but they also safely transported the French participants to the RRI without getting lost. So they're one of the organizing team. And I have very strong theory collaboration with Shobhan Datta, in-house theorist, and Rajesh Nath, who is present here. And so I come to the summary of my talk. I give an introduction to Rydberg atoms, and then I showed some of the results in our experiment, including Doppler enhanced quantum magnetometry, then observation of the effect of strong interatomic interaction between Rydberg atoms, and then I quantum sensing of microwave fields with Rydberg atoms, and then I gave future perspective on quantum information, quantum sensing, and quantum many-body physics with ultra-cold Rydberg atoms. Thanks for your kind attention.
Thank you very much, Sanjukta. Do we have questions? Yes.
Thank you. At some point you mentioned that you have this ultra stable cavity, and that you lock your laser on it. But this is to lock one of them, I guess, on the transition. But what is important for EIT is the two-photon detuning, right? So that the both lasers are phase locked.
Yes, so what we do is like we we lock one of the lasers to the cavity, and then we have a piezo on the cavity, and then we tune the cavity to see the spectroscopy signal, and then we lock the laser, and then we lock the other laser to the cavity. So in this way we lock both the lasers.
So you lock both lasers on the same cavity?
Yes, yes. So they are custom made. The mirrors of the cavity are custom made for both 960 and 780.
Okay, so you basically use it as a kind of frequency comp?
Yeah, yes.
Another question?
Maybe just a query. You showed a reference for paramagnetic to spin glass phase, something like that.
Yeah.
Who is the author of that? Actually, I don't see.
I forgot the author name. Please, you can look up.
And what? No, I'm saying how they will detect that transition, quantum phase transition.
Yeah, I mean, this was predicted for Rydberg atoms. We have to go to the details of this paper. So
no, but I'm asking, do you know that in what they were proposing to probe, or you?
So I have not gone into the details of this paper, but yeah, I mean, but what I'm showing this because I see a possibility to look at this very interesting spin glass phase using ultra cold Rydberg atoms.
Yes, a question there.
Thank you, Sanjukta, for your very interesting talk. I think we'll have a lot of time to discuss because your research subject on metrology is very close to mine. So I wanted to go back to your Outler-tone splitting measurement with as a function of the principal quantum number, where you see broadening. But if we look carefully, we also see some shift and shift of the center resonance, slight shift. Did you explore the origin of this shift?
Yes, so we have discussed this in the paper. So it's because of the imperfection in the experiment, we should not, see a shift in principle. So
Okay.
at least, I mean, for the theoretical modeling, I mean, we should not see a shift. So because, we tried to keep the Rabi frequency, as perfect as possible. So we made sure that as we go to the different principal quantum number, we keep the Rabi frequency same. So we tried it as much as possible, but the shifts are because of some imperfection, which is out of the experiment.
But in your theoretical modeling, we see that the center of the resonance is shifting. Is it just to reproduce the experiment, or is it like?
Yeah, this
for
is we have taken some parameters from the experiment to
Okay.
to so that so because we are exactly fitting it with the experiment, so we have taken use some parameters to get it to fit it with the experimental result.
Okay, and at some point you showed that the noise on your Outler-tone splitting improved due to the, yes, perfect. So do we agree that the splitting of the Outler-tones feature is dependent on the laser cooling, the cooling laser power and detuning?
Yes.
But here we observe a change in the splitting.
Yeah, because the laser was very unstable and it was going all over the place without the locking. So that's why it's a completely noisy, unstable signal. So it's just a comparison. So this was locked and we know the frequency was stable, but this frequency which was not locked, it was going all over the place. So this was just to show how effective our cavity locking is.
But the cooling laser was before locked on saturated absorption, or was it just
so
free running?
as I said, that the cooling laser was first locked to the cavity, and then with the piezo of the cavity, we locked it to the saturation absorption peak.
I see. Okay. Thank you.
Do we have another question? Yes?
Just a quick question. So when the principal quantum number increases, the gamma started increasing at one point, right? So do we know any idea about the Rydberg blockade size or Rydberg atom size at that stage?
So the rule of the thumb is like at 100 100 n equal to 100, the range of blockade radius is like around 10 micron or so.
Okay.
So it's of that order.
Okay, so I think we have to thank the speaker again and close this session. We are a bit late, so I don't know what we do with the break.
cannot do anything. So the organization teams, do you have all the slides ready, a list? What can we do together? And the list of the people so that I can call them maybe. Do you have it? Ah. I don't know. We need to stop at 6:30 and it is? We have 40 minutes and here I have, oh, who can count? 1, 2, 3. Well, I think, let's call people in order. So Fabien is first, then Romain, then Nikos. So Fabien, Romain, Nikos, Niranyan, Shriganesh, Elwin. So let's start by Niranyan has also a talk, right? So Shriganesh, Elwish, Devati, Parmajit, Nargis, Adrien, Meduna, Arnab. Arnab has a talk, has he? No. Yeah, so Arnab, come. Anthony, Nishant, Boja, Aishwarya, Shruti, Ashta. You got all the names in order? And we'll have Fabien, Romain, Nikos, and I'm not there. I should be there. I don't know, whatever. So we are starting by Shriganesh. Does that work? Shriganesh, okay. Elva, it's Devati or Revati, I don't know. I'm not sure. D. Yeah, 17. Okay, it's you.
I can connect HDMI.
And people in the audience can rank the level of dress up of people from the French delegation coming up. Elwin is going to win, this is why. Yeah, but Juan is not up. He was in the first presentation. Okay, tic-tac, let's go.
Okay. Good evening, everyone. Thank you, organizers, for giving me a chance to present my research. I'm Sri Ganesh, and I'm working with Professor Ambarish Ghosh from IISc. And I'll be talking about electron phase-dependent instability pathways of multi-electron bubbles in liquid helium-3. So multi-electron bubbles are basically bubbles inside liquid helium in which the inner surface or the interface is covered with electrons, and these can be generated by hydrodynamic instability of charged liquid helium surface, and they can be trapped using planar Paul traps. So in this case you can see 3 bubbles trapped stably. And my experiments basically involve generating, trapping and observing them and see what happens. So because these electrons are trapped on the interface, they form a 2-dimensional electron system, and you can calculate the different parameters of these bubbles. The key thing is that with time, the vapor inside the bubble can condense and the size decreases, which results in increase in the electron density. And we can have a phase diagram that determines the phase of these electrons inside these bubbles. So depending on the density and temperature, you can have these different phases. And in the community of electrons trapped on liquid helium, only this lower part of the phase diagram has been explored experimentally. And our main goal is to look at the high density region of the phase diagram. And the main idea is by looking at these collapsing MEBs, we can basically go up in density and possibly explore these unexplored regions. So to do that, we have to ensure that MEBs are stable, but if you calculate the energies, it turns out they are metastable. and you can write down equations to see what happens if you perturb their shapes. So it turns out as the vapor content reduces, even if you apply a small amount of perturbations, they can undergo a parametric instability, and which can result in the bubble splitting into two equal halves. And that is what we observe at high temperatures. There is no surprises here. So you can see the videos. I'll just wait for one of them to split into two equal halves. And that's how they become unstable. So there is a limit to the minimum size that the bubbles can achieve. But in this intermediate regime, as the bubbles condense in size, this is what we observe. So initially they go up and down very smoothly, but beyond a certain size, they show this jerky motion which starts right about now. So that's a completely different behavior compared to how it was in the beginning. And this is basically can be explained by taking into account that the electrons inside have undergone a phase transition from a liquid phase to a Wigner crystal phase. And the bubble takes irregular shapes because of the sudden breaking of the Wigner crystal. And in this way, we have ways to experimentally measure the charge and density of the electrons inside these bubbles. And we have seen these bubbles in this region of the phase diagram for the first time. And this is also the first experimental signature of Wigner crystallization on of electrons confined to a sphere. But below 1.2 Kelvin, we see a different type of instability which cannot be explained by any simple classical theory. And we are still trying to understand why this is happening. And we have some connection, this has some connection with how charged droplets become unstable. Even this also has no simple theory, like why charged droplets don't become unstable just by splitting into two equal halves. So if you want more details, you can visit me at the poster. Thank you.
Thanks a lot. So this is poster 15. So make your notes. And now 16 is Elwin. Run, run, run. There is no transition in the transition. Ignore the transition. Thanks. It looks like what they do with race car. People are changing the wheels while others are filling the fuel again. And now the driver is entering the car. Wrong.
So, hello, I'm Elvin. I'm from India, as you can probably even already guess. And I'm from Bombay. If you, just for our French colleagues, we are currently here, and I am from this part, which is to the west of India. I've done my bachelor's there in Bombay from St. Xavier's College, followed by a master's at the Indian Association for the Cultivation of Science, which is to the east of India in Kolkata. And just as a small caveat, this is also the place where Sir C.V. Raman did his groundbreaking Nobel work, and this is the original spectrophotometer that he used to get the Raman effect. It's still preserved at IACS. And then after that, I came back home to Bombay, to TIFR, to do a small stint on atomic magnetometry. And what I'm currently doing for my PhD is somewhat of interest to the magnetometry community. And that is, we study atomic correlations using this technique called spin noise spectroscopy, where we had two fantastic talks today morning. So I'm doing my PhD under the supervision of Fabienne, who is one of the organizers, and Nikos, who is also having a talk this week on collective effects. And we also have a talk by Advait, who is the postdoc with whom I work. He will be talking more in detail on spin noise, the work that we do at Lumen. So this is our building at Arce, which is 30 kilometers to the south of Paris. And as Fabienne already mentioned, you have a very good connectivity by the RER from Paris to Arce, so it's quite convenient for us. Yeah, exactly. So since we already had good talks on SNS, I'm not going to go much into the details of the thing, but it's basically just to, again, recap. You have noise in your atomic ensemble, for example, transit and spin exchange, and this noise induces circular birefringence in the medium. And if you have a linearly polarized light, you have this Faraday rotation. And if you have a fluctuating population, you have a fluctuating Faraday rotation. And you can use a balanced detection scheme to convert these polarization fluctuations into power fluctuations, and you ultimately detect it. So since the sample is unpolarized, you have a mean spin to be 0. Therefore, you get a peak at the 0 frequency, and the spread is due to the noise sources. And of course, we don't like to work at 0 frequency due to technical reasons, so we just apply a magnetic field and we shift the frequency to some higher Lama frequency. So this is the typical spin noise signal that you would expect in a non-interacting case, where the line width is set by all possible relaxation mechanisms. Now what we want to do at Lumen is to use this spin noise spectroscopy to try to study atomic correlations. And one way to do it would be to get the atoms very close by to increase the number density such that the interatomic distance becomes less than an optical transition. So to do that, we use temperature as a knob, and you can increase the temperature up to high densities. And how we do this, we have it more on the poster. But just a small teaser, at low densities where the atoms are far apart, they are not interacting, you have the standard spin noise signal. But if you go higher to these high densities, you can observe two dramatic changes. First is the line broadening. You can see this line has broadened. And this baseline is no longer flat. You have had a slight increase. So these are two dramatic changes that you observe as you get the atoms closer. And we have attributed these to resonant dipole-dipole interactions happening inside the vapor. And we have conducted a bunch of other experiments to verify and support this claim, and the experiments do support this claim. And there is also a theoretical model that was made by the student before me, and that model can partially explain the dipole-dipole interactions, but then there is still work to be done on this, on this low-frequency noise, and we would be open to discussions from people who are working in collective effects, for example, to discuss things like light trapping, multiple scattering, and so on inside the vapor. And this could also be of interest to the condensed matter community, because you can study your many-body effects with simpler atomic systems. So please do visit. We are just here at poster 16, which is just this side, and see you there. Thank you.
So that was 16, and there's an archive too, even though it didn't say so. And now we have 17, which is Bevati, and we go. I have no funny noise to make, but you can suggest any animal you want.
Hi everyone, I am Revati. I am a postdoc here in the Theoretical Physics Department in RRI. So my poster is about my postdoctoral work with Professor Shovan Datta in the Theoretical Physics group. And we work on shaping magnetic order by local frustration for itinerant fermions. So basically what we do is we bring together the fields of network science and quantum magnetism to ask this central question, that is how collective quantum mechanical ordering of a many-body system is governed by the underlying geometry or the network topology. So, or basically in simple terms, is it possible to tune the connectivity of a network in order to shape the magnetic ordering in a system? So the answer is yes. So we consider a system of strongly interacting electrons with a single mobile vacancy or a hole that can move across the network to induce magnetic order through a phenomenon called quantum path interference. And we show that local frustration centers, for example, so this is a very schematic diagram of our main result. So through local frustration center, I mean odd loops present in the network, which causes frustration. And so we show that local frustration centers binds singlets. These green dumbbells are the singlets. And the frustration centers bind singlets, while the hole is delocalized throughout the network. So this here, the red dots represent the whole population throughout the network. Yeah, so the central result is that local frustration centers bind singlets while the whole is being shared throughout the lattice, throughout the network structure. So by this remarkable property allowing for collective organization, allows us to produce predictable changes in the network topology predictable changes in the magnetic order by changing the network topology. So this allows one to engineer desired quantum states by just tweaking the geometry. So for more details, do visit our poster, which is poster number 17. Yeah, thanks.
Thank you, Revati. And I see there's an archive too. You put the reference. So now we have number 18, Dr. Parmajit Banger. You're a doctor too. They didn't put a doctor to you.
Hello everyone, my name is Paramjit. I'm working as a QC Breeze postdoctoral fellow at IIT Roorkee with the Professor Ajay Vasan. And okay, this is my current research group where all the students are PhD scholars. So here we focus on the realistic multi-qubit theoretical system because most of the theoretical proposals and work related to multi-qubit system, they have considered this ideal blockade. But when we talk about the practical experimental things, there are always some blockade, finite blockade strength, which leads to create some population leakage and creating some errors which create some unwanted accumulated phase and eventually end up with the deterioration in gate fidelity. So here we consider the ideal system with under some finite blockade, and for that we simplify our model by converting our system into the symmetry adapted basis. And from this we can see like there is a few states which are directly coupled and few states which are decoupled. By using this Hamiltonian and the full system, we have studied like how much population leakage we observed for our system and as a function of finite blockade strength, and what fidelity we observe, and how much error we get in this system. So this work is very useful for the guidance of scalable quantum computing. So I'm not going to discuss here in more detail. So I welcome you all to poster number 18, where we can discuss in all detail. Thank you.
Thank you very much. Poster 19, which is Nargis Sultana. Oh, she wears the best dress.
Hello everyone, my name is Nargis Sultana. I am currently a PhD student and I'm working with Professor Rajesh Nath from IISER Pune. So recently we published a paper in New Journal of Physics with my collaborator and colleague Siddharth Sitaraman with Professor Rajesh Nath. So the system that we are studying is basically two spin J particles. These spins can be, we have just generalized it to any value. So what we are doing is basically we are taking these two spin J particles and they are interacting through the dipole-dipole interactions, and they both are simultaneously subjected to a rotating magnetic field, which is of the form this B. Which has a transverse field component B perpendicular, and it is rotating in this XY, the transverse field component is rotating with rotation frequency omega. So to model this, we have this Hamiltonian, the Zeeman component along with the dipole interactions. So the main our main focus was to study how much maximum entanglement we can generate between these two particles. So across different rotation frequencies. So to study this, when we analyze this setup with two spin half atoms, which is the simplest case, what we found is, so basically we are plotting here the maximum entanglement entropy between these two particles, which we are defining as the entanglement entropy is just the von Neumann entropy. So if we plot it across different rotation frequency, we see some peaks at the maximum entanglement entropy taken over a certain time period. And as we increase the transverse field strength, these two peaks merge together and we get something like this. So these we are calling it as resonance. Another striking feature that we got is this presence or emergence of kinks, which is basically in this for a certain field parameters, the transverse field and the longitudinal field, at certain frequencies, we get a very sharp dip in this maximum entanglement entropy, which we are calling it as kink. And interestingly, we found that this is a very sharp dip, and exactly at this field parameters, the dynamics of the system is governed by a single frequency dynamics. So we analytically got the exact condition of getting this kind of kink in our system. Similarly, we have extended our work for spin 1 and spin 2 also, where even though the Hilbert space became larger, but still analytically we found and we could identify few of the entanglement resonances for spin 1 and spin 2. And we also proposed an idea to use these kinks which can be useful for entanglement engineering. And we saw here that if we have a dynamically changing rotation frequency of this magnetic field, and if we hold on to this rotation frequency at the kink, we can actually control the generated entanglement between these two particles. Whereas if you are a little bit shifted from the kink position, the generation of the entanglement is like less controlled. So of course these kinks can act as a tunable knob for precise entanglement generation. So thank you for your attention, and you can visit my poster. It is poster 19. Thank you.
Thank you. So this was poster 19, as said. Poster 20 is Adrien. At some point, we'll stop not to rush the last people, and we'll find another slot at some other time.
Hi, so I'm Adrien Gavalda. I'm in my last year of PhD under the supervision of Antoine Brouez and Igor Ferrier-Barbu. The lab is situated in the south of Paris, like many other people here. So it's what I would present for my poster, and I actually also have a talk on Saturday, is collective spontaneous emission. So I think you are all familiar with spontaneous emission of a two-level system. And it's characterized by two things. So for a single atom, spontaneous emission, you know for the time dynamics is an exponential decay. And for the direction of emission, it's essentially isotropic. More precisely, it's a dipolar pattern, but whatever. So what we study is not a single atom spontaneous emission, but collective spontaneous emission. And it's really the textbook example. You really have, this is a cloud of two-level atoms that is actually quite extended. It's not sub-wavelength. And we want to characterize the time dynamics and the emission pattern. So for the time dynamics of such system that you start by inverting all of the atoms, you wait, and you see where the photons go. So radially, you will see the characteristic exponential decay, but where it gets interesting is when you look along the axis. Here you have essentially stimulated emission. This is why you will have an increase of intensity initially instead of the decay, and then finally the decay because you have finite energy in the system. All right, but this was already known for many years, actually, for like almost 50 years now. So what we want to know is what are the direction in which the photons are actually emitted. So the emission pattern, is it still isotropic or not? Clearly it's not, because you have two different dynamics in two different directions. So what you would expect probably is to see a peaked emission, something isotropic background, plus a peaked emission along the axis. And we can actually precisely measure that. And the way we do it is with a Fourier image of the plane. By putting a lens right at the distance of the focal distance of this lens, we can map direction into position on a camera, and then we just take a picture of the photon that have been emitted throughout the decay, spontaneous decay. And what we measured 6 months ago was actually quite surprising, because it was not just peaked on the axis. There was as you can see here, a small hole in the middle. And if you want to understand why it's there, why it's not just a peak, like a Gaussian pattern, come see my poster or the talk. Thank you.
Thank you, Adrien. So yeah, there is a talk, and this was poster number 20. 21 is Miduna.
Hello everyone, I'm Mithuna. So this is my master's thesis work under the guidance of CM Chandrasekhar at IISc. So I worked on deterministic quantum phase estimation with linear gate complexity in photonic system. So quantum phase estimation is a fundamental algorithm in quantum computing that tries to estimate the phase of an eigenvalue for a given unitary operator. So the computational circuit of the standard QP circuit is this. It has a sequence of Hadamard gates, then a sequence of controlled unitary and inverse quantum Fourier transform. But the circuit complexity of the standard QP is to the order of n square. So this poses a challenge in scalability and experimental implementation. We found out a class of unitary operators. If we use this as the unitary operator, then we can optimize the circuit and the gate complexity reduces to order of n, which is linear complexity. Yeah. So for example, for the case of 4 control 4 target, which is like 8 qubits, this is the standard QP circuit and this is our optimized circuit. And we implemented a 4 qubit circuit using photonic qubits. And we encoded the first 2 qubits in path degree of freedom and the last 2 qubits in polarization degree of freedom. And that's essentially 2 interferometers. So yeah, for results and discussion, please come to my poster. Thank you.
Many thanks for this very efficient presentation to Miduna poster number 21. 22 is Arnab.
So, hello everyone, good evening. So, I'm Arnab Maiti. I'm a second year PhD student in the Quantum Gases group in Laboratoire Charles Fevre in Institut d'Optique, which is situated in the south of Paris. And my supervisor is Marc Chenot. So, as you can see, I am from India. And especially I am from West Bengal. And I also studied in West Bengal. So, I completed my bachelor's and master's from ISAR Kolkata. So just I want to introduce to you all about my poster, and I also have a talk on Thursday afternoon. So we are building a new fluorescence microscope for strontium-84 atoms in the optical lattices. So optical lattices are periodic potentials that are created by interfering laser beams, and we can put bosonic strontium atoms into it. And this can be well described by the Bose-Hubbard Hamiltonian. So I will not go into the details of the model. So just that, so you can see a quantum phase transition at 0 Kelvin temperature from superfluid to Mott insulator. And in the superfluid regime, like the atoms can freely travel between the neighboring lattice sites. And if you go to the Mott insulating state, then the atoms are kind of fixed in the lattice sites. And we want to actually investigate what happens in the quantum critical region here, because the low excitations of the systems will be highly correlated and shows universal behavior. And for this, we want to build a quantum gas microscope. So quantum gas microscopy is basically a fluorescence microscopy of atoms. So atoms are trapped in the optical lattice. And then we excite fluorescence, and the photons are collected using a microscope objective. And here the information is the occupation of the lattice sites. So you can get this kind of picture from a quantum gas microscope. So I said so there is a new fluorescence microscope. So I will tell what is new in our setup. So in our microscope we have shallow optical lattices which has a trap depth around 50 microkelvin. So this is because we want to make a very large system, and as a consequence, we have shallow lattice depth. People usually use a very larger trap depth, around like a millikelvin temperature. So there are some drawbacks that comes from the shallow optical lattices. For example, we have to laser cool the atoms during the imaging if we want to keep the atoms trapped during the imaging. Also, we have a very simple imaging setup. We have a single aspheric lens inside the vacuum chamber. And so in this talk, also in my poster, I will explain if we can really image the system with shallow lattices, and also if we can get images of atoms using a very simplistic imaging system. So to give you some teaser, we have already observed side resolved imaging of strontium atoms. Here, each single dot you see are single strontium atoms. and also we have been able to see quantum phase transition from superfluid to potential state. Yes, thank you.
Okay, so thank you very much. I just need mine to be put up, and the people who didn't talk now will have their chance. We are taking a slot before the gala dinner tomorrow. No, because I want people to have the time, not to be the last one. It would be so. In any case, tomorrow we'll be together at the Mysore, and just before gala dinner, let's say at 6, if we will see what time we are back, time to shower, blah blah blah. We'll meet again at 6 and finish this session. We're starting with Anthony, Nishant, Bhumicha, Aishwarya, Shruti, Ashtar, and then Fabienne. They wrote Fabienne, so Fabienne is coming, right? Romain, Nikos, and Niranyan. I just wanted to, so this doesn't matter. Can I have the next one? Okay, breaking all the rules, chairing myself. So just wanted to say that in my themes I love multicolor rainbow thing. So we can choose to do this, each keeping their thing. You can choose to see things like that, it's a mess, or we can try to do this kind of stuff. So for this, these are my kids' toys, of course. So for this we suggested these show and tell sessions. And so here are some suggested themes, and I suggest you take your camera out and take a picture of this, and take the time of the excursion or tonight or whenever you want to think about it. And these might be the things we could discuss together. So there is one cluster about technical points. So we realized we all had something clever, or some rage to vent out about factor of 2 and these theoreticians. Maybe atom cells, there are some technical transverse points we want to discuss. People who are especially proud or especially ashamed of the way they found ways to process data. Whatever you found is some technical issue that could interest many. So we're physicists, many is 2, huh? 1, 2, many. 3, okay. So that could be something. Another cluster could be, what you think makes you special or your group special. It's not something you boast at in a conference or in a journal, but you think you made a very good job at mastering cake contests, diversity initiatives, or you've been especially bad at it, and maybe you have some best practice to spread about it. You are a master of Arduino or something else. Something that, so how to read this sentence? Something you realized about theory that changed your life as an experimentalist, something you realized about experiment that changed your work as a theoretician. So H bar is not equal to 1. Fingerprinted specificities, that's one. And maybe we can, at some point, discuss together perspectives, which is a big word, to say, what sounds to you as a big roadblock and or paradox. Is there something that you actually never understood, that people claim that it's going to work, or, I don't know, ions are the best qubit? Is this really true? Let's be provocative. What surprises you? So some easy sentence would be, something that surprised you. Like, how did this paper get published in Nature? How did this paper didn't get published in Nature? It works both ways. Is there some understated results that you noticed or some overstated trend, some misconception that you think could be around? So anything that could go in that. So we'll try to organize. If you have, so I put this one randomly, the poor Alan is going to be overflowed, but let's try. This is the address to send one slide, and maybe it could be just one sentence, like, let's talk about atom cells, I have something to say, 2 bullet points, something like this, and we'll try to discuss along this thing. So maybe I suggested this organization, that's a technical point, and or that's something specific about my group, or this has to do with perspective of the field, something like this. So just decide, so blue, green, or red. If you don't agree with this classification, that's fine. You can create a purple, and we'll make a purple group, but it's just, so just I wanted to say this session requires your active collaboration, but you don't need much to present. So just to say, looking at little bits of the pictures we had, anything is a poster, anything is a slide. So if you just want to show a photo, a printed figure of a paper, this is why we called it show and tell. And so these were, the generic advice I sent at some point in the emails to the French participants, but maybe never got to talk or say explicitly to the whole audience. So thank you for this. And Fabienne has something to say.
One thing, there will be, we change, because of the jet lag for Fabien, it will be hard to have the first talk on Thursday. So there is a change with Athanasios, who will have the first talk at 9:30 on Thursday, and Fabien will be not the next one, the one after the break. Thank you.
So everyone is tired. Summary. We now meet at the main gate to get to the Four Seasons for whoever dressed well enough. And people who get kicked out will have a party in the center of Bangalore, and this will be fun. Tomorrow, we reconvene here at tentative time 6 to finish this poster session after the Mysore excursion. So I am in charge of spreading information among the people from France, and once I have the information, Sanjukta will have it and it will spread. So please be there whenever is the right time. So we're planning down to Wednesday, and Thursday we will start with Athanasios, and Fabien will be the next Athanasios. Yeah. But this doesn't matter to you. There was a swap in the schedule, so something else to say, yes. So tomorrow, what should we do? Dress up, have good hiking shoes. What do you say, Sanjukta? It's a city tour, I get to understand, so no strenuous hiking.
Yeah, wear comfortable clothes and shoes. It's going to be a long day, but it... Huh? Yeah, you can take umbrellas because there's a very huge ground in front of the palace. You may, want to be there. It's very pleasant to be there, and so. Yeah, it can be hotter than Bangalore. Bangalore is quite cool, and so there will be, lunch in between, and so the tour is all scheduled. You just relax and enjoy the tour. You don't have to worry about anything, and so I think the vehicle will be here at 8:30 in the morning. So the breakfast will start from 7:30 onwards. So you can have your breakfast and be in time at 8:30 for starting to Mysore. And there will be tourist guide right from here. So there will be a French-speaking tourist guide in your vehicle. So he will explain not only places in Mysore, but also on the way. And